on the behalf of the organizers, I'd like to wholeheartedly welcome you all in the webinar Recent Development in Molecular Catalysis 2024. We all know that molecular catalysis plays a large role in both academia and industries, where having precise control over chemical reactivity is the key. So in fact, nowadays, molecular catalysis has become an indispensable tool for the synthesis of specialty chemicals, agrochemicals, pharmaceuticals, having complex molecular structures. So to get an update of the recent developments on molecular catalysis, CSIR-CSMCRI Bhavnagar, in association with Indian JSPS Alumni Association, has organized this webinar. The principal aim of this webinar is to bring together both experienced and relatively junior researchers of the field from all around the globe. The webinar is consisting of 3 sessions. So in each session, 2 speakers, one from India and one from Japan, will deliver their lectures. Here, I'd like to mention that we have invited relatively senior speakers for the first, second sessions compared to that of the third session. So I sincerely hope that this event will give a platform to the research scholars, faculty members, and other research personnel in the field to develop knowledge on molecular catalysis. So with this brief introduction, may I now request Dr. Kannan Srinivasan, Director CSMCRI, to give the formal welcome address of the webinar. Please, sir.
Thank you, Dr. Sukalyan. At the outset, I sincerely thank the Indian JSPS Alumni Association for giving us the opportunity for organizing this webinar on recent developments in molecular catalysis. And I also sincerely thank all the invited speakers, Professor Methi, Professor Ishiara, Professor Mukherjee, Professor Hayashi, Professor Maji, and Professor Sai for accepting our kind invitation to be part of this webinar. I sincerely welcome all the colleagues who have joined online on this webinar, both from the Institute, the CSIR Central Salt and Marine Chemicals Research Institute, Bhavnagar, and all the other participants across the globe, because this was widely circulated in the both in the print as well as the social media. And I hope that many young students, researchers, and senior level researchers are those who are interested to know about the developments of molecular catalysis would be attending this session. And I sincerely welcome all, both from India as well as from abroad, because this topic is something which is extremely important for our planet on the whole. And I also take on this occasion to welcome the chairpersons of this session, Dr. Ganguly, Dr. Subramaniam, and Dr. Adimoti, who are accompanying this webinar along with me from this conference room physically. When Sukalyan was discussing with me what is the kind of a topic that we should choose for this webinar, we had a kind of an a small brainstorming, and he has, he is basically an organic chemist, has some amount of knowledge on catalysis, though he basically builds molecule. Catalysis he uses as a tool, and we said, the organic chemical synthesis in the last few decades are sincerely having a kind of a love for the molecular catalysis, and that's what we said. We should have a kind of an understanding on how this molecular catalysis has helped in the recent years for advancing the science, and also, as Dr. Sukalyan was pointing it out, how it is going to help the industry and in turn on the society on the whole. In fact, I don't want to tell this audience, but being from the catalysis background, which is my core expertise for roughly 3.5 decades, I strongly believe for the growth of a nation, any nation for that matter, or for that matter, the UN Sustainable Development Goal, which is 17 in its nature. I believe catalysis can play a very, very significant role. Okay, any molecule that we are going to touch, any product that we are going to use, any component that we are going to consume, catalysis is going to have a significant play on that. And I don't have any iota of doubt on it. The numbers also speak. The kind of an industry that it is catering, which is, if one were to look at it, the effort with which the catalysis is making will be one of the the top 10 countries GDPs, if one were to take it. Okay, catalysis can be basically placed in one of the top 10 countries in terms of its GDP contributions. So that's the kind of a power with which catalysis is playing a stellar role in our lives. And the molecular catalysis is a subset of it, which is which gave birth in the early part of last century, but really picked up with a kind of an in parallel advancement of both significant analytical tools and also computational power. Both were basically started happening in the mid of the last century, when these understanding of exploring that a single molecule with a defined chemical architecture can do the same thing as a kind of a complex heterogeneous catalysis, which involves multiple component species, for which understanding becomes still more complex. Okay, that is the that is the kind of a transition which has happened in the molecular catalysis space. And the most important feature for taking molecular catalysis forward is because of the precise control it offers. Okay, and this precise control can be tailored or customized by choosing appropriately, which is largely a kind of organometallic catalysis and off-late organic catalysis. In the last 2-3 decades, we have entered into a kind of an organocatalysis space. But if you really see, the precise control, the precise stereochemistry, the precise position of the functional groups, the precise nature of the functional groups, the precise stereochemistry of the functional groups governs in terms of rightly forming the molecule of the desired choice. And this is extremely important, where the single molecule based effort, be it in the case of the pharmaceutical, be it in the case of a fine and specialty chemical, be it in the case of the agrochemical, where a kind of a single molecule is going to make a kind of a difference for a given designated purpose, and the precise control being a kind of a characteristic requirement, and molecular catalysis can play a kind of a stellar role. And further, if one were to look at it, understanding of the mechanism of molecular catalysis is reasonably simpler compared to that of heterogeneous catalysis. Even after the discovery of 100 years of Haber-Bosch, ammonia synthesis catalyst, still, the research is ongoing in understanding how the structures and functions of different kinds of the materials have a kind of an interplay in controlling the reactivity and in turn on the desire for improving the catalysis. On the contrary, molecular catalysis offers a kind of a good understanding in terms of mechanistic insights. And through these mechanistic insights, one can always make a kind of a differential characteristics for tailoring. Suppose, for example, I wanted to insert one particular moiety in a particular position. the understanding of the mechanism will give you a kind of a clues and understanding based on the fundamental principles of chemistry, where we can design. Okay, theoretically we can design, and experimentally we can synthesize and make these kind of a molecules and then try out for these reactions. And this is exactly, and this particular challenge of designing, discovering, designing, and implementing gives a kind of a tremendous amount of scope for molecular catalysis. Of course, needless to say that these molecular catalysis are extremely used in the industrial space also. A large number of molecules are used. The simplest thing, okay, if one were to do, is a kind of a simple metal salt catalysis, which started, several decades back, which even some of the organic chemists even today also follow, is a kind of a fundamental understanding of the a single site catalysis concept, which is for adding a kind of an organic moiety along with a kind of a metal, and see how the stereochemistry, how the electronic property, how the structural features can be turned in making the chemistry very interesting. And more importantly, the molecular catalysis offers tremendous amount of turnovers. In the other word, a single site can regenerate millions of times to make a kind of a conversion of a desired molecule of A to B, which is extremely difficult in the other kind of a catalysis. And that's the, we rarely see a paper which is involving a molecular catalysis, which is having a turnover number citing in tens or hundreds. They always tells in thousands and millions and that kind of a number. What it precisely tells is, as a molecule, if I'm basically making a structural motif, and if a reactivity is controlled through a kind of a precise nature of the molecular catalysis, a molecular catalyst that I'm engaging with, these sites regeneration for making activity through a kind of a desorption of the product molecule, since most of them happens in a kind of a single phase, largely in the liquid phase, it becomes easier for the molecules to dance around and then convert themselves in a kind of a great propensity. On the contrary, the number of hit on a heterogeneous catalyst surface and the conversion of those molecules into a kind of an active, product molecule has been very less compared to that of a molecular catalysis control. And that's the advantage it has. And the importance is felt. In fact, when I was browsing through the catalysis related journals, the fact that the Journal of Molecular Catalysis started way back in 1975, the first issue of the Journal of Molecular Catalysis, way back in 1975, when a reasonable amount of computation had just begun in 1970s, and also advancement in terms of analytical tools have just begun in 1960s and 70s. The reasonable resolution spectroscopy and microscopic investigations have just begun, and molecular catalysis birth in terms of journal is also understanding the importance of how the molecular catalysis will shape the planet. And that's the way that this field has grown. And we will be the Elsevier should celebrate the molecular catalysis 50 years next year, hopefully. And this clearly tells that the importance of this field. And the speakers today are going to basically tell about different. I browsed through a kind of all the 6 titles. And all of them are, extremely interesting and challenging, and have a kind of a significant implications, whether it is for the chemical industry, or whether it is for the energy industry, or whether it is for, pharmaceutical industry. The nature, the kind of a science that they are going to discuss for the next 3 hours is going to make enriching our expertise and experience on that domain. And hopefully, the students and the young researchers who are attending this meeting who will get a kind of a benefit and get a kind of an inspiration to start their career in some of these exciting domains. With this, I once again welcome you all for this webinar, and I sincerely thank the Indian JSPS Alumni Association, especially Dr. Sakti Kumar, for choosing this institute as a host for organizing this webinar. What do you do?
So thank you very much, sir, for the nice address. So we will now move forward. So may I now request Professor Dr. Shakti Kumar, President IJAA, to deliver his remarks. Professor Shakti Kumar, please.
Hello, am I audible?
Yes.
Oh.
Please go ahead.
Hello, thank you. So, Dr. Kannan Srinivasan, Director some CRI, Dr. Sugalyan, all other distinguished speakers, scientists, and students. I'm really thankful, particularly to Dr. Kannan Srinivasan, for allowing us to organize this seminar in your institute. Because for the past 2 decades, I was trying to do some organized seminars in Gujarat and that kind of areas for the past 2 decades. I could not do that. So by opening this seminar, you yourself and Dr. Sugalyan helped us to open the way to enter in Gujarat. I'm really thankful. I hope this will bring a lot of Japanese professors, Japanese scientists into the region to have more collaborations in the field of science and technology, as India and Japan now vigorously working to improve and increase the collaboration with India's leading national research institutes and, of course, Japanese National Research Institute. Recently, I'm going through a lot of discussions with the Tokyo University, Hokkaido University, and many other universities doing, which clearly shows that most of the Japanese institutes are really interested to be in connection with the Indian institutes. So that way, I was a little bit worried earlier why this Gujarat and that region is totally not in our radar. So, but now with this seminar, you have opened the channel. And I would like to give some information about what Indian JSPS Alumni Association is doing for the past about 2 decades to increase the interaction between India and Japan. So let me share our, just very briefly, I will go through that.
Yeah.
I hope now it's visible, right?
Yes.
Is that okay?
Yes.
Okay, thank you. Thank you. So this Indian JSPS Alumni Association started in 2006 because I came here as a JSPS fellow in Japan in 2001. And after finding that, still there's no such good collaborations and interactions between India and Japan is not working. And I thought that starting an alumni association would be a better option to create such environment between India and Japan. So for that, actually, we started our website, and anyone who is interested to see our most of the work, please visit our website. We have cataloged almost all our work, which we have present, which we did for the past 2 decades. So our executive body is well spread all over India, having many of them are directors, chancellors, and some of them are the top decision-making bodies in India. And we do have developed 4 chapters. I also have North, West, South, and East chapter. And based on that, we are doing a lot of India-Japan seminars from 2000 onwards. So far, we have conducted around 13 India-Japan seminars in India and about Nobel laureate seminars in online as well as in Hyderabad too. So that means we have conducting this seminar for 2010 onwards. And this year in 2024, we are going to organize our 14th Japan seminar at Guwahati from 6 to 7 September. So this seminar we are going to organize as a part of in Japan month celebrated by Embassy of Japan in New Delhi. So these are the three seminars we conducted based on our Japan 60th and 70th anniversary in diplomatic relations. And you can see here now, this is what I was mentioning. Picture is very clear that what we were doing to conduct our India-Japan seminars. We were visiting many other places in India to spread the awareness of JSPS, JST, and the different Japanese universities' activities to our Indian audience. Because when we started around 2006, 2010, we came to know that our students in India is not that much aware of what's happening here in Japan. So to clear that kind of situation, we started to organize India-Japan science seminars almost all parts of India. So maybe you can see from the picture that I could not break even after doing a lot of seminars in these areas. Gujarat particularly I'm looking for. So all other places we conducted our seminar, and with this one maybe coming next year or in years, we will also be able to conduct our India-Japan seminars in Gujarat and nearby areas. So as last year, we found that though we are conducting these seminars for more than 14 years, and some of the places which we are not penetrated, like which I have mentioned in Gujarat, this time we wanted to do some small-scale seminars, like some of our dignitaries and others could not reach the places very easily due to the travel restriction or travel problems or something like that. So we started this year onwards our new initiative, chapter-wise seminars, 2 seminars per chapter, in total 8 seminars. So under this, we have conducted already one seminar under a North chapter in March 11th, and another one in South chapter, and this one is actually we are conducting our 3rd seminar in West chapter. So again, 5 more seminars in queue, and we are going for that. So these are the some of our activities. You can see here, we do a lot of programs with our students. We call Indian students to give the information about our Japanese universities information. And these are the seminars which we conducted. And see, we'll also do some cultural programs, poster presentations, and Japanese universities information and fellowships to the Indian students, etc., etc. So you can see some of the activities. So to expand further, this is very important for Japanese delegates, Japanese professors. So we started India-Japan Society for Science, Technology, and Education, established in 2024 in January. This is particularly for professors from Japan who hosted Indian JSPS alumni members, and also Japanese professors, Japanese students, and the Indian professors and Indian students working here in Japan. We are planning to bring almost everyone in under one umbrella so that we can proceed further. Already, His Excellency Ambassador C.B. George already became the patron, as well as current president of JSPS alumni, JSPS Sugino Tsuyoshi also accepted to become patron of this our new society. So under this program, we are going to establish a lot of similar kind of seminars which we conduct in India. The same will be conducting here in Japan too. So I request all Japanese professors and their friends and their students to join this association. So once again, I welcome you all to 14th India-Japan Science and Technology Seminar going to conduct September 6 to 7 in IIT Guwahati, Assam. So together, we will work together to increase India-Japan science and technology collaborations in near future. Thank you. Thank you very much. Once again, I thank you to Dr. Kannan Srinivasan as well as Sugalyan to organize. Thank you. Thank you very much.
Yeah. Thank you very much, Professor Kumar. We will now move forward to the technical sessions. So I'd like to request Dr. Vishwajit Ganguly, Chief Scientist and Senior Scientist of CSI CSMCRI, to chair the first session of the webinar. Dr. Ganguly, please.
Thank you, Dr. Sukalyan. Good morning and welcome to RDNC 2024. We have 2 esteemed speakers in the session 1. The first speaker is Professor Developents from Indian Institute of Technology, Bombay. For the benefit of younger audience, I'll just read out the brief CV of Professor Maiti. Professor Development Maiti received his PhD from Johns Hopkins University in 2008 under the supervision of Professor Kenneth D. Carlin. Afterwards, he moved to MIT for his postdoctoral studies with Professor Stephen L. Buchwald. He joined afterwards the Department of Chemistry at IIT Bombay in 2011. His research interests are focused on the development of new and sustainable synthetic and catalytic methodologies. Professor Maiti has received many national and international prizes and fellowships, including the Santi Swarup Bhatnagar Prize 2022 by the Council of Scientific and Industrial Research. Professor Maiti also served as an associate editor of the Journal of Organic Chemistry from 2018 to 2023, and currently he is editor-in-chief, Synlet. Today, Professor Maiti is delivering a talk on unlocking new chemical space via selective catalysis. Platform is yours, Professor Maiti.
Morning, everyone. Can you hear me?
Yes. Please go ahead.
Hello.
Yeah, we can hear you.
Okay, great. Thank you. Thank you, Mr. Chairman, Dr. Ganguly, for this sweet and kind introduction. First of all, I would also like to thank Sukalyan for arranging it perfectly for all of us and in giving me this wonderful opportunity to present here today. Thank you, Directors CSMCRI Bhavnagar. Thank you to President IJAA for kindly hosting all of us today. Morning again to all my dear friends, colleagues, speakers, and students, and all the attendees over here. So today I'll briefly discuss over next half an hour or so the ongoing. Yes. Okay, I'll discuss part of the research that is ongoing in our laboratory at IIT Bombay. As Dr. Ganguly mentioned, we are mainly working in the domain of catalysis. One of the domain in the catalysis that we are presently trying to work on is this carbon-hydrogen bond activation. Some of you may be familiar with a little bit what we are trying to do. Essentially, it's a domain which has become active over the last 2-3 decades, although in different form it existed before. But in recent literature, we have seen tremendous growth of this domain. Simply speaking, if you look at organic molecule, there are aliphatic substrates and aromatic substrates. Aliphatic substrates are more exciting for its selective carbon-hydrogen bond activation and extremely difficult to do the activation and subsequent functionalization. For aromatic substrates, it's relatively, I would say, compared to aliphatic substrate, it's relatively straightforward. It has usually 3 to 4 different type of carbon-hydrogen bond, and therefore one perhaps can strategize and try to look if we can selectively functionalize these different bond. The main carbon-hydrogen bond that is usually being activated and functionalized is the ortho-CH bond or ortho-carbon-hydrogen bond of an aromatic substrate, right? Usually we have seen with a metallocycle formation, 5 to 7 member, sometime it can be even bigger. One can activate the ortho-CH bond of an arene, but it was little bit difficult to do the meta as well as para or any other carbon-hydrogen bond that is present into the aromatic substrate. Now, usually, what we have seen in last several years, many of us are involved in designing a ligand. Sometimes we are calling it as a directing group or DG or template or simply a ligand. We are attaching a ligand or designing a ligand and then attaching with the organic substrate. And therefore, that becomes also the limitation of this approach. Once again, what we are doing, many of us in the community, we are trying to take the organic substrate and trying to design a ligand or directing group with the organic substrate. And then due to its precise designing, we are expecting that metal will be placed in a desired position. For example, either meta position or para position. In our group, we have been actively working in this domain. We are trying to make sure that the ortho-CH bond or para-CH bond is not getting activated with a series of different ligand. For example, this is the best ligand we have so far, and also perhaps the best in the literature so far, where you can take this ligand and attach with the organic substrate, and kind of assuredly one can do the activation at the meta position. If we are looking for para-CH functionalization, the design of the ligand has to be a little bit different. I'll come in a moment. And any of these ligand, let's say particularly the second generation template, if any of these template or ligand is attached with the organic substrate, then the ortho-CH or meta-CH bonds are usually not activated, and one can deliver the metal precisely at the para position. Okay, let me come to it little bit more detail. So what we are trying to tell you is, many of us in the literature, we are trying to take the organic substrate and designing ligand. In this case, this is the brown color partner is the ligand here. With this ligand, as you can see, the designing is overall such that the metal will be bound with the ligand in a monodentate fashion. I think that is one of the key factors. The ligand has to be monodentate because mainly we are dealing with palladium as the metal, palladium 2+, which is the active species for carbon-hydrogen bond activation. It's a D8 square planar species. That means only 4 coordination can be accommodated at the metal center. Now, out of these 4 coordination, we will have at least 2 coordination from 2 incoming substrates, or the substrate or the cross-coupling partner, right? And usually another ligand is also necessary for carbon-hydrogen bond activation. That can be a monodentate or bidentate ligand. But put together all these requirements, we have maximum 1 coordination available for this so-called directing group or template that you see here, a biphenyl pyrimidine-based template. We try to take and design this ligand in such a way so that you have 2 nitrogens. So statistically, even if 1 nitrogen is missing, at least you have the probability of finding the metal as well as placing it in the right position. Not only due to the probability factor, also this makes the ring little bit more electron deficient, making this ligand overall good sigma donor as well as pi acceptor, meaning that despite being a monodentate ligand, still metal and ligand association can be strengthened. In addition to that, of course, the substitution pattern in both the top and bottom ring has to be perfected, which we did by iterative experimentation as well as modeling studies. At this point, we are reluctant to change way too much on this scaffold, so that we know that any changes either going to give us lower yield and lower selectivity. I think it is clear that if you are missing in designing the template clearly, then we will end up getting orthoselectivity or mixture of product formations. Okay, now the ligand, despite being monodentate, what we are finding that it is still good enough to ensure that the carbon-hydrogen bond activation happens rather easily. Even in a lot of cases, we are finding with this ligand, it is no longer the rate determining step. It's important to mention that we try to characterize each of these intermediate, the first form, second one, and before reductive elimination, all the steps we were trying to characterize in detail, and detailed kinetic studies all are done. It allows us to better understand the reaction mechanism as well as the product formation. If there is any side product formation, also usually we are able to rationalize. But overall put together, what we realize that this sort of ligand is good for metal like palladium. If any other metal need to be used, usually one need to change the designing of the ligand, because this is specifically designed for palladium. Well, it has been a challenge so far to incorporate the first row transition metal so far, often needing multidentate ligand, and positioning of the metal are critical so far, and a lot of activities are going on the background to make sure that the first row transition metals are working in this part or in this sort of activation. As I was mentioning, we have been working on the para-CH functionalization or selective para-CH functionalization. You see here the designing is completely different. In this case, from the template or from the substrate, the template is really placed outward, and this biphenyl cyano template is making sure that metal is held perfectly and can be delivered at the para position. Once again, all the designing principle comes into picture, because this is going to be a huge metal cycle. As you can see here, from the organic substrate, template is going out and coming back, overall giving a D-shaped template. And we thought that a pi stacking interaction will be beneficial, free rotation will be critical, having this dimethoxy substitution and the hydrogen bonding that can go on, just like 2 nitrogen in the previous slide. Hydrogen bonding with the solvent will also be critical in rigidifying the substrate, and having these 2 isopropyl group and the impeding Thorpe-Ingold effect will also be critical for bringing the substrate and template together. So again, we can come back perhaps in the discussion section about the designing of this ligand. Almost everything that one can think of need to be perfected and improved upon iteratively, and then only it was possible actually to see that the metal is precisely placed at the para position without touching much of the ortho or meta-CH bond. Well, once the activation and metallation can be achieved, one can then do the selective functionalization at those positions by using the organometallics techniques. Now, well, both these approach, the meta-CH functionalization or para-CH functionalization, as I mentioned, the major drawback still remains for this domain simply is you need to attach and detach the template. And as synthetic chemist, none of us are really super excited about it, because it would be requiring attachment and detachment like protection and deprotection type of chemistry. Additionally, usually almost for the entire domain of research using the palladium chemistry, of course, it's not limited to just palladium. You can have palladium and rhodium chemistry parallelly going, and we can have the benefit of both the palladium and rhodium chemistry. But one of the major limitations that we find simply is we also need to have the silver salt for the regeneration or for the last step. Usually 3 equivalent, sometimes 3.5 equivalent silver copper salt combination need to be used. Also, we require very high temperatures such as 90 to 130 degrees centigrade for majority of the palladium catalyzed CH functionalization, or even many of the rhodium catalysis. Okay, so we were thinking, can we not do something about these limitations? Okay, so once again, we need to attach and detach the template, which deters synthetic chemists to use this methodology effectively, and the reaction condition itself, silver salt and high temperature need to be looked at. Of course, there are perennial issues such as use of high catalyst loading that also need to be looked at, and these are roughly the limitation if one is able to overcome some of this, perhaps this method can be synthetically useful both academically and industrially. Okay, let us look at one at a time. First of all, as I was telling, we need to take the organic substrate, attach and detach. Can we not have an in situ attachment and detachment? So towards this, simply speaking, we thought that we will take an aldehyde and amine as a combination. So aldehyde can be the substrate, amine can be the template or the ligand, right? You see the ligand designing is influenced by our previous studies where covalent linking was really explored. Now we see when we have taken aldehyde as a substrate and amine as a ligand, we can form the in situ imine. We do not have to have this preformation covalent linking, and we can do selective functionalization at a desired position. In this substrate, you see there are 5 to 7 different types of carbon-hydrogen bond that is present, and selectively this highlighted carbon-hydrogen bond can be activated by the similar approach as we have seen. But in this case, the template can be brought in without preformation, in situ formation, in situ imine formation can be done. Well, as I was mentioning, the reaction conditions still need to be improved. But what we fail to impose simply here is we couldn't really get the imine formation reversibly. Means aldehyde and amine forms the imine, do the reaction and hydrolyze reversibly and in a catalytic manner. That we were not able to achieve. We can do maximum a stoichiometric reaction with respect to the ligand. All the previous things that I have discussed, of course, these ligand need to be stoichiometric. That remains another limitation. So what we have recently done, we tried to look at our previous scaffold, what we were doing. Now you see, as you have seen in the previous slides also, this is the substrate and this is the template we were attaching together. What we have done very recently is we are able to cut it open and we have taken the ligand separately. Now in a catalytic fashion, I think again this marked a contrast with whatever we and others were doing in the domain. We were taking stoichiometric amount of ligand. Now we are able to take a catalytic amount of ligand, as you see in here, and through anionic hydrogen bonding, we are interacting with the organic substrate. Now this substrate can be amine, like benzyl amine, phenethylamine, phenpropyl amine, and so on. But utilizing this weak interaction, which we see quite often in the enzymes, we are now able to dictate the position of the metallation and subsequent functionalization. Once again, I repeat, this is something what we have been trying to do for long, where we would like to take the organic substrate in stoichiometric amount or whatever amount we want for its distal carbon-hydrogen bond activation, utilizing a weak interaction such as the anion hydrogen bonding interaction. In this case, we are able to show that we can still take the metal center and place it in a way which essentially mimics the way enzyme is operating. Through weak interaction, we are able to coordinate the substrate and template together, and that too template in catalytic fashion. Okay, I'll again can come back later if you have further questions, but essentially the chemistry remains similar, a metallocycle formation and metal delivery and subsequent functionalization. One also may be thinking, can we not do this chemistry with hydrogen bonding, just like what we have seen in organocatalysis, and then bringing the organometallic chemistry together? We have been working on it for quite some time now. What simply we are able to show that substrate, like let's say nitrobenzene, it can undergo hydrogen bonding with urea-based motif. And with this urea motif, if we are attaching the template can hold on and deliver the metal at a position of our choice. And therefore, a distal, such as let's say meta-CH bond in this case, can be activated and subsequently functionalized. If you see over here, Also something like ketone functionalized aldehyde, ketone, ester, and amide all can undergo hydrogen bonding with this urea motif, and with an appended template, we can then deliver the metal at the distal position, right? So all these put together, we believe we have, or we are working towards making this template catalytic. In all these cases, the template, as you see, the hydrogen bonding template appended with this organometallic moieties, where you have a nitrogen palladium interaction. This whole entity can be made in catalytic fashion. So catalytic template can be utilized now. In addition, we are now able to do these reactions under relatively milder condition. I will come to that again. And we can incorporate nitrobenzene, aldehyde, ketone, ester, amide, amine. So a variety of substrate, no longer requiring covalently linked template, which we have been discussing for last 5, 7, 8 years. And these recent exploration actually hopefully pave the way to make sure that a variety of organic substrate can be functionalized selectively in a manner which synthetic chemists would like to use. Well, one of the major limitation, another major limitation that we have been facing and we were trying to overcome, is how to ensure that the superstoichiometric amount of salts, such as silver salt or silver copper salt, may be avoided during these reactions. Once again, silver and palladium or silver and copper salts are used for oxidizing the palladium 0, which is generated in the reaction mixture. So it's a palladium 2 as the starting point, and it ends up having palladium 0. Overall, it's a palladium 2-0 catalytic cycle, unlike cross-coupling reaction, where it's a palladium 0-2 catalytic cycle. In the carbon-hydrogen bond activation, it is a palladium 2, palladium 0. Now, we need silver and copper, or most often 3 to 4 equivalent of silver for this step, and this is not that very efficient step. Well, we thought that if we have a suitable photocatalyst which just confine itself in this last step by combining with oxygen, perhaps then we can oxidize palladium 0 to palladium 2. Okay, and that is what we tried to find out. We tried to find out a suitable photocatalyst, and we see that a series of simple photocatalysts like Eosin Y, Rose Bengal, and so on can indeed do this job of oxidizing palladium 0 to palladium 2. In addition, we thought, can we not have a suitable palladium ligand complex which will be able to absorb the light, and from the photo-excited state, we will be able to activate the palladium ligand complex, and then we will be able to do this reaction perhaps under the room temperature, as opposed to the very high temperature like 90 to 130 degrees C that we are using often for the reaction. Right. So to keep the long story short, simply speaking, by taking a suitable ligand palladium complex which can undergo photoexcitation, and from photoexcited state we are able to do the carbon hydrogen bond activation, meaning that very high temperature that we were using can be now turned into a photo and room temperature reaction. Both thermal as well as photo energy will be used. Thermal energy will be used in the form of room temperature, usually 30 degrees centigrade or so, and photo energy can be utilized from the simple household bulb. All we needed to do is to choose the right palladium ligand complex. Now, since we are now able to do this reaction under room temperature and so-called oxygen-free, or by using oxygen and photocatalyst, we are then using relatively milder condition. That essentially means that the reactions previously, which were happening at very high temperature or somewhat high temperature and with superstoichiometric amount of silver, now we can do these reactions at room temperature and oxidant-free condition, and these milder reaction condition, meaning that we are not having much of an issue of the regioisomer formation. Well, no matter what usually we or anyone else are trying in this domain of carbon-hydrogen bond activation, what we often see, in addition to the main or the major product, we are bound to form some minor product or the regioisomer, right? So the major product is formed. Along with that, the minor isomers are also forming. And we thought that that is mainly because of the fact that we are hitting these reactions quite high. And if we can do these reaction at room temperature or under low temperature, so the minor product formation pathway may be retarded or, kind of perhaps suppressed, can be suppressed completely if we have sufficiently low temperature. Indeed, that's what we have seen. This is an excellent work in 2017, which gives a number of products in addition to the main product, side products we are forming, now doing the same reaction, which is popularly known as Fujiwara-Moritani reaction, or greener version of the Heck reaction. We are now able to do selectively only one product formation thanks to the room temperature reaction, as well as doing this reaction without silver. Right. Overall, putting these all together, we can showcase the scope of this reaction to be quite broad. Not only it is limited to these sort of non-directed CH functionalization, we can have the directing group as well, meta, para, or any ortho-directing group, even the asymmetric catalysis by utilizing CH activation, all can be done quite effectively. To keep it short, we have a palladium ligand complex, photoexcited, and from a photoexcited intermediate, only 18 kcal per mole roughly is required for the CH activation. Otherwise, it was requiring 45 kcal per mole at thermal energy, which is now can be split into photo plus thermal energy, and therefore thermally only 18 kcal per mole is required, which is sufficient to be promoted at room temperature. Just to sum up, that rest of the step works out similar to what Heck coupling or Fujiwara-Moritani reactions are over there in the literature. So to sum up this part, what we are trying to tell you simply is a suitable ligand palladium complex can absorb light, can be photoexcited, and from that photoexcited state, we can have only very limited amount of energy, which is sufficient to promote the desired functionalization. And if we are able to do that, then we can do these reactions quite comfortably at room temperature. Okay. Now, very quickly, I'll get into a related domain, which is the activation of carbon-hydrogen bond of aliphatic substrate. This has been a challenging topic in the literature, and it is very much substrate control. There are many different positions, unlike aromatic substrate. Aliphatic substrate, you have alpha, beta, gamma, delta, epsilon, and so on position. But more importantly, even every position can have a primary CH, secondary CH, or tertiary CH, right? That makes it even more difficult for doing the selective functionalization. For example, we wanted to have a way to do the secondary CH or methylene CH bond activation to synthesize these sort of lactone natural product. There are many natural product which has this sort of lactone moiety, right? If you take any of these, let's say I'm taking the last one and try to do a retro analysis, we immediately find if we can form a bond between these carbon oxygen, then we will be able to do the CH bond functionalization and this lactone synthesis quite easily, right? Now, the problem simply here is this position is gamma with respect to the acid. Acid can be a ligand, so alpha, beta, and gamma position. This is gamma CH, and also this methyl is gamma CH. Usually what we have seen, not usually, I would say almost always, if you have a gamma methyl versus gamma methylene, always this methyl gets activated, and therefore the lactone formation cannot be done. Okay, just to tell you that we have methyl and methylene, the same thing as you have seen earlier. If you put a metal center such as palladium under suitable condition, this methyl CH bond can be activated, but you are going to form a spirus. You are not going to form a lactone that you want for natural product synthesis. You can have a spiro compound here. Now the issue simply here is, although this methyl activation is easy, what we realize that carbon-oxygen bond formation step or the reductive elimination step is difficult. So this intermediate can be formed very easily, but since there is no beta hydrogen, alpha position, beta position, since there is no beta hydrogen, there is no other pathway for any other product formation. It has to undergo this, carbon-oxygen reductive elimination. We are then, or we then realize that they're actually an opportunity to do this methylene activation under this condition, which is typically known as Cartin-Hammett situation, where preferred intermediate is not undergoing reductive elimination, and then this non-preferred or relatively less preferred intermediate can be generated. Fortunately for us, there is a beta hydrogen. Over here, there is no beta hydrogen present, and therefore no other side product can be formed. Since there is a beta hydride elimination pathway available, we are able to promote this beta hydride elimination more effectively by using a bulky ligand, and then subsequent rollover metallation can be done to form this bicyclic lactone motif. So once again, this is a typical Cartin-Hammett type of situation where the main intermediate or the first form intermediate cannot be taken to the product, and the less preferred intermediate can be taken to the product. Okay, and as you can imagine, by utilizing this method, one can synthesize a variety of natural products. Okay, I think I was a little bit slow. I have few more slides to discuss on a little different topic, and that is the final topic today. In 2-3 minutes, I'll try to wrap up. I think all of us over here are familiar with cross-coupling reaction, which involve oxidative addition, transmetallation, reductive elimination, roughly in this step, and many of these seminal work has been discovered at Japan. So I'm really lucky to have many colleagues, friends in the society where we regularly interact and discuss about this development. These cross-coupling reactions essentially change the way synthesis is done, change the way people look at the organometallic chemistry, right? There is nothing wrong in it, but as we all know, there are certain limitations even in these best reactions on Earth. That is cross-coupling reaction, one of the best reactions, definitely. That simply is that we need to have an electrophile and nucleophile and a lot of difficult substrate combination, like let's say heterocycle combination, 5-member heterocycle with multiple heteroatom, and so on and so forth are not working in this case. Let me focus on one of the limitations, and that is you need an electrophile like aryl iodide or aryl bromide, and a nucleophile like, let's say, boronic acid, aryl zinc, lithium, you name it, different cross-coupling reaction, different nucleophile. Now the availability of the nucleophile is rather little in the literature, in the commercial scale, right? What we thought, if we can take two electrophile, any of these two electrophile, and can combine, perhaps this could solve some of the problem that cross-coupling is facing. But the main issue simply here is, let's say, if we are trying to cross-couple between aryl iodide and aryl bromide, these different 5 products one can get. Heterocoupling is the desired product, just like Suzuki coupling, Nigisi coupling, Hiyama coupling, any Stille coupling. So this is the product we want, but along with that, these 4 products, homocoupling and proto-dehalogenation, is the problem. To some extent, by taking Nigisi type of reaction, this is solved, but again it uses 5 mole% nickel and palladium with super stoichiometric amount of zinc, but it is again the Nigisi coupling type of reaction. So what we thought, can we not have 2 halides two different halides, right? And combine them by using one metal ligand system. So we wanted to have a ligand palladium complex which is able to absorb light, right? And this is going to be something different what we see in the literature in terms of cross-coupling reactions. Cross-coupling reaction usually or always, almost always utilizes palladium 0-2 catalytic cycle. But with suitable ligand palladium 0 complex with a photo-excited intermediate, we can engage one of the most reactive partner. It need not be aryl iodide. One of these partner, which is more reactive, can undergo radical palladium 1 intermediate, which can be characterized. And the other one, of course, has to be also reactive enough and compatible enough under the reaction condition to undergo oxidative addition. So we have a palladium 0-1 cycle started, and we have a palladium 0-2 cycle as well. Together, so there are a lot of things has to be placed correctly. Together, if it has enough lifetime, it should not undergo homocoupling or proto-dehalogenation. If it is really having enough compatibility, we may then have an opportunity that two of these can combine. And if this formation or if this step is facile compared to the proto-dehalogenation and homocoupling, then we have an opportunity to have a new type of intermediate, which is, let's say, palladium 3 intermediate, as opposed to palladium 2 in the traditional cross-coupling. And then the reductive elimination can give the product. Okay. Well, to keep the story short, yes, by optimizing and foreseeing all the problems that this process can provide, as you can imagine, 5 different product formation can be possible. We were able to almost minimize or suppress all 4 other side product formation, and we are able to get this cross-coupling product. Design of the ligand and improvisation of the reaction condition was required, but I'll keep it short, that we are now able to overcome some of those limitations that existed in the literature. And this is, of course, going to be a growing field, at least in our group, where we find that different heterocycle coupling can be achieved, which were limitations in the existing cross-coupling reaction. And even the bioorthogonal chemistry at the very beginning can also be introduced by utilizing. So this need to be explored in further details, and a lot of planning, both in terms of ligand designing and mechanistic understandings, are ongoing in the laboratory. With this, I would like to thank again all the organizers, Sukalyan particularly, for giving me this opportunity, and all of you for listening to me. None of this would have been possible without enthusiastic support from all the funding agencies in India, DST, SERB, CSIR, BRNS, and also to all my collaborators, without whom none of these collaborative and detailed mechanistic understanding would have been possible. And thanks to my students, who are really the people who are doing this chemistry. Just a quick one, we are having a IASCHA International Symposium on CH activation from December 6th to 9th at IIT Bombay. Please do join us. We look forward to welcome you at Mumbai. And with that, thank you once again, and I'll be happy to have any question if there is, or if time permits. Thank you very much again.
Thank you, Professor Maiti, for your insightful talk. As we are running behind the schedule, so probably one or two couple questions we can take quickly. Participants can raise their hand if they have any questions. Oh, raise hand option is there. You can choose and raise your hand.
I have one question.
Yeah.
Professor Maiti, I mean, I think a fantastic piece of work, especially the last piece of work on coupling of aromatic halides through kind of a palladium 3 ligand cycling, which is something which is very, very kind of a weird approach. Is there have you I mean, what do you call identified the formation of the palladium 3 through any spectroscopic means?
Well, that's a very important question. Yeah, this is something we are still struggling to characterize palladium-3. No, we haven't. But some of the other intermediates we were able to characterize spectroscopically. Palladium-3 we are not able to characterize so far, but we are thinking to independently synthesize by an alternate route and trying to promote this intermediate to show the compatibility of the reaction intermediate for the product formation. But so far from the reaction mixture directly, we are not able to characterize palladium-3.
Okay, fine. Thank you.
Thank you.
Okay. So there are no more questions. I'd like to thank once again Professor Maiti for his excellent presentation and sparing his time with us today.
Thank you.
Thank you, Professor Maiti.
Thank you very much. Thank you all.
Our next speaker is Professor Kazuaki Ishihara. Professor Ishihara is currently professor at Graduate School of Engineering, Nagoya University, Japan. His early education was also in Nagoya University with Professor Hisashi Yamamoto, where he did his Bachelor's of Engineering to doctoral degree with the same under the supervision of Professor Hisashi Yamamoto, Nagoya University. And 91-92, he moved to Harvard University, USA, for his postdoctoral studies with the Nobel laureate Professor Elias Shekori. And after a brief stint, he returned to Nagoya University as an assistant professor in 92 and rose to the position of full professor in 2002 in Nagoya University, Japan. He has several awards and accolades in his career. I just name a few. In 1996, he received the Young Chemist Award for the Chemical Society of Japan, the Chemical Society of Japan, the JSPS Prize 2005, 2024 ACS, Swiss Chemical Society Lectureship. His principal areas of interest are the rational design of high-performance catalysts based on acid-base combination chemistry. Professor Ishihara is one of the well-cited chemists in the world today. His H index is around 89 with 288 original papers, 140 review articles, and 87 patent applications. Today, Professor Ishihara will deliver a talk on rational design of high-performance catalysts based on acid-base combination chemistry. Professor Ishihara, please.
Thank you for the kind introduction. So, okay, first of all, so I'd like to thank organized committee for giving me an opportunity on this occasion. Today, I'd like to talk about rational design of high-performance catalyst based on acid-base combination chemistry. Okay. So this is our classification of acid-base catalyst. We can classify two types of acid-base catalyst. One is ion pair catalyst. This type of catalyst can be prepared from acid and a base. So if we use strong acid and a weak base, so salt is also acidic. So if we use weak acid and strong base, so salt catalyst is basic. Important point is active site is located at the center of salt. So we can.
Professor Ishihara, sorry,
yes?
Probably your slides are not moving. Can you just check that? You are on the second slide or first slide?
This is second slide.
Oh, we cannot see the second slide.
Oh, I see. Sorry.
Yes.
Ask him to use only the slides sorted.
Professor Ishihara, possibly you can use the left pan, where you can see the number of slides and you can manually change the slides.
Okay.
Okay. On the left side.
Yeah, it's working.
Yes.
Okay.
This way. Thank
yeah.
you.
So this is our classification of acid-base catalyst. So one is ion pair catalyst from acid and base. Okay. So another is acid-base cooperative catalyst. So in this case, we introduce acid and base in one molecule. Usually, so we introduce weak acid and base So this type of catalyst can work as a dual activation catalyst for many reactions. So this is conjugated interactive acid and base catalyst. So in this case, this is mono conjugation of acid and base. This is double conjugation of acid and base. This is triple bond conjugation of acid and base. So this type of catalyst works as a dual activation catalyst to stabilize a concerted cyclic transition state. So we can control size of catalyst for each size of transition state. And also we can design of supramolecular catalyst based on small molecule of acid and base. So to construct deep chiral cavity, and also we can apply charge relay type of system using acid-base combined catalyst. Okay, today I'd like to talk about two topics. So the first topic is enantioselective radical cation 2+2 and 4+2 cycle addition of carbon derivatives by chiral iron photoredox catalyst. So key is control of radical cation counter anion ion pair. We want to introduce chiral counter anion to induce enantioselectivity for 2+2 and 4+2 cycle addition. Okay. So radical cation species, which is prepared from alkene with oxidative initiator, is very attractive as a active material for active starting material for 4+2 and 2+2 cycle addition. Already, so many oxidative indicators have been developed. So, for example, this is a radical cation induced 4+2 cycle addition. So this reaction is very attractive. So because this reaction proceeds with electronically mismatched radioselectivity under thermal condition. So under thermal condition, so this type of radioisomer should be obtained. But if radical cation species is generated, so opposite radioisomer should be obtained. So this chemistry is interesting for me. So we focus on iron chloride, trivalent iron chloride as an oxidative initiator. So because iron chloride is very cheap and very familiar as an oxidant, already many researchers use iron chloride for biaryl coupling reaction. Usually, so excess amount of iron chloride are used, but corrected mechanism is not known. So because we don't know the actual structure of radical cation species. So at first we want to focus on the structure of radical cation species. So we designed a very bulky electron-rich aromatic compound. So then we add 2 equivalent of iron chloride to give a radical cation species. So this compound, so this ion pair could be isolated as a single crystal structure. So this is the first X-ray crystal of radical cation species. Now we can understand what is a counter anion. Counter anion is an iron tetrachloride, this one. Then, so we developed radical cation 2+2 cycle addition and 4+2 cycle addition using a small amount of iron chloride or iron triflate. So iron triflate and iron perchlorate are more active as a oxidative catalyst. So we can find several chiral natural compounds, so bearings, so cyclobutane structure. So we want to focus on radical cation 2+2 cycle addition to synthesize these compounds. So we can compare photo 2+2 cycle addition and radical cation 2+2 cycle addition. So this key intermediate is a biological species. So in this case, so usually diacetyl selectivity is not so good because this bilateral coupling reaction is not so far, not so fast. So rotation is much faster, and then diacetyl selectivity is not so good. But in this reaction, key intermediate is a dystonic radical cation species. This coupling reaction is much faster than this biological reaction. So usually, so in this case, so diacetyl selectivity is much higher. So this is one of the reasons why we focus on the radical cation 2+2 cycle addition. So Professor Nisbets reported the first example of enantioselective radical cation 4+2 cycle addition using chiral oxopyrenium photoredox catalyst, this one. Okay, so they use this catalytic amount of chiral oxopyrenium photoredox catalyst and at minus 60 degree for 3 days under blue light irradiation. But the enantioselectivity is not so high, from 0 to 50% EE, not so good. So recently, actually last year, Professor Benjamin List reported highly enantioselective radical cation 2+2 cycle addition using very bulky counter anion and oxopyrenium cation complex. So this reaction, high enantioselectivity was observed, but the condition is not so good. Minus 100 degree for several days are required. So they used the same alkene as an electron-rich alkene. So our idea is different. So if we want to introduce electron-deficient moiety to anetol derivative, probably counter anion radical cation distance should be shorter than that of this ion pair. If we introduce chiral counter anion, probably asymmetric induction should be more effectively induced. So we designed this type of dienophile. Okay. So this is a first reaction of 2+2 cycle addition of chalcone derivative with chlorostyrene using iron chiral phosphorus imide. So this imide complex is generated from iron chloride and silver salt in situ at minus 40 degree. But actually, so very low EE was observed. So just a moment. Okay, so actually very low EE was observed, but if we irradiate blue light, so this reaction dramatically accelerate, and higher enantioselectivity was observed, so 28% EE. So we screened chiral counter anion. Then finally, we found triisopropylphenyl substituted octahydrovinyl is a best ligand of iron. Okay, so if we use this type of iron salt, so even at minus 40 degrees for 1 day, so high reactivity and high enantiomer selectivity were observed. So this is a good substrate scope. And also we can screening this aromatic moiety, so no problem. So we determine the absolute configuration by X-ray crystal analysis. And also under same condition, 4+2 cycle addition can occur with good to high enantiomer selectivity. Okay. So anyway, what is a real counter anion of radical cation species? One is a ligand anion. Another is a iron tetra chiral phosphoramide. Which one? So, so we prepared chiral oxopyrenium chiral anion salt. So this is the same chiral anion under the same condition. Almost same enantiomer selectivity were observed. So 2+2 and 4+ cycle addition. So now we can understand. So even in the presence of iron salt, still counter anion of radical cation is chiral phosphoramide, not iron salt. Okay, so anyway, so we prepared chiral oxopyrenium chiral salt by ourselves. So this is commercially available, but a very expensive compound. So we prepared by ourselves from this one and this one, but yield is not so good. So even in this reference, so yield is from 5 to 35%. Then, so under basic condition, so diketone was obtained in low yield. So this is our result, 21%. So according to Nisebet's paper, 40% this compound was obtained. Then, so with mixed chiral imide, so this type of photoredox catalyst can be obtained. So total yield is not so good. So I think so iron salt is more practical. So just this is a control experiments. So in our case, so para-alkoxy moiety is required as a substrate. So in the absence of alkoxy moiety, so this electron, pi electron is not so enough. So under the same condition, no reaction occur. Okay, and also if this part is methyl, not electron deficient carbonyl moiety. So actually, so Professor Nisbet and Benjamin List used this substrate. In this reaction, under the same condition, only 8% EE and low yield was observed. So benzoyl moiety is important for inducing high enantiomer selectivity. This is a UV-Vis analysis of iron salt. Okay, so just we mixed 1:1 of iron chloride and the silver salt, 1:2 mixture and the 1:3 mixture. So blue light is here. So from 1:1 to 1:3, so 1:3 salt is most effective for absorption of blue light. So I think so under blue light irradiation, so iron salt is excited. Then, so this type of substrate is oxidized as a radical cation species. So this is a Stern-Bolmer analysis of this substrate and this substrate and in the presence of iron salt. So according to this analysis, so electron-rich carbon derivatives should be oxidized. Then radical cation species generated, and then so this radical cation react with chlorostyrene to give this type of compound. And also this is an interesting result. So this is the best result. When I used 1,2,3 mixture of iron chloride and silver salt, best enantiomer selectivity and yield were observed. But 1:1 mixture, so low yield and 0% yield was observed. 1:4 mixture, in this case, so silver chiral silver salt is excess. So almost the same result with 1:3 mixture. So 1:3 mixture is important for exciting. So under blue light irradiation and inducing high enantiomer selectivity. So this is our proposed mechanism. So initially, chiral iron salt should be generated in situ from iron chloride and 3 equivalent of silver chiral silver salt. And then under blue light irradiation, so this iron salt is excited. Then, so alkoxy carbon derivative is oxidized to generated so radical cation species. So counter anion is chiral phosphoramide. So chiral phosphoramide induce enantiomer selectivity. So this is a stepwise mechanism. At first, radical coupling reaction occur with this one. Then, so dystonic radical cation species are generated, and then so iron salt, divalent iron salt is oxidized to trivalent iron salt to generate the desired product. Okay, so this is a summary of the first topic. So key is introducing carbonyl moiety. So by introducing carbonyl moiety, so the distance between chiral counter-anion and radical cation is shortened. So then, so higher enantiomer selectivity can be induced from chiral counter-anion to product, even at -40 degrees for 1 day. So key person of this project is Assistant Professor Shuhei Omura, and graduate students Katagiri and Akao also contributed so in this research very much. Okay. Second topic is chiral macrocyclic catalyst for enantiomer selective addition of lithium acetylide to ketone. So key concept of design of catalyst is a charge relay system. Okay. In 2000, Professor Kagan reported this type of reaction. This is an enantiomer selective trimethylsilyl cyanation of aldehyde, so using lithium vinyl. This is a very simple reaction, but enantiomer selectivity is not so good, 56% EE. So they reported in 2000 Then so we have interested in this chemistry. Then we follow this reaction at first. So we found, so in Japan, if we follow this reaction, very high enantiomer selectivity was observed. So what is the difference? France and Japan. So Japan is always very high humidity. So in Japan, so our students follow this reaction, but they cannot keep dry condition. So actually, a small amount of water or alcohol is very important for inducing high enantiomer selectivity. So we published this paper in 2005. So water or alcohol is very important for the aggregation of lithium vinylate. Under anhydrous condition, lithium vinylate is tightly aggregated. So this is a disappointment for inducing low enantiomer selectivity. Then in 2011, so Professor Nakajima reported an interesting result. They used 3,3' diphenylvinyl as a ligand of lithium. So nucleophile is alkynyl lithium to ketone. So they succeeded in high enantiomer selectivity and high yield for ketone. This is a very interesting result because ketone is low reactive, and enantiomer selective control is usually very difficult. But unfortunately, substrate scope is not so good. For example, so isopropyl phenyl ketone. So reactivity is okay, but enantiomer selectivity was only 7% E. So when I read this paper, so I think so even in this case, so aggregation of lithium vinylate is a problem. So at first I wanted to add appropriate of water or alcohol, but lithium alkylate is unstable or protic solvent. So what shall I do to suppress aggregation of lithium vinylate? So our idea is a macrocyclic ligand of vinyl. So macrocyclic ligand suppress self aggregation. Then maybe higher enantiomer selectivity and reactivity can be observed. So we expect it. So macrocyclic ligand is easy synthesized from vinyl. So at first, so acetylene moiety is introduced to 3,3' position of vinyl, and then quick reaction to give a macrocyclic compound from C12, CH212 to C24. Okay, so total yield is not so bad. So this is an X-ray crystal analysis of C20 alkyl chain. So interestingly, one intramolecular hydrogen bonding is existed here, but another side, no hydrogen bonding. So not cis symmetric conformation. Okay. So we examined Nakajima type of reaction using phenyl cyclohexyl ketone as a substrate, using phenyl alkynyl lithium in THF-78 degree for 5 minutes. When we use C20 alkyl chain ligand, so this type of product was obtained in 95% yield with 97% E. But other size of macrocycle from C12 to C19, So reactivity and the enantiomer selectivity were dramatically decreased. And larger macrocycle, C21 and C24, gradually reactivity and enantiomer selectivity are decreased. And also, crown ether type of macrocyclic ligand. If we use this type of ligand, no catalytic activity was observed. And also acyclic long alkyl chain is here, no effect. So in this substrate, if we use Nakajima type of ligand, 5% and 10% E was observed under the same condition. So without catalyst, so reactivity is not so good, only 11% E. So this type of ligand is very effective for acceleration of reaction and inducing high enantiomer selectivity. Okay, so this is a proton NMR of Nakajima type of dilithium salt. Okay, so broad peak were observed. So this means that aggregated structure. How about our C20 type of dilithium salt? Still not so simple. Actually, this is a mixture of monomer and dimer. So homodimer and monomer, okay? But the monomer is a major. So we checked nonlinear effect of this alkynyl addition reaction. So positive nonlinear effect was observed when we use C20 ligand. So this means that racemic dimer was almost inert. So monomeric monomer should be a real active ligand for this reaction. Okay, this is substrate scope. So not only alkyl phenyl ketone to isopropyl and vinyl phenyl ketone and cyclic ketone are available as a substrate. And also tertiary butyl ketone is also available, but enantiomer selectivity is moderate, but reactivity is not so bad.
Professor Ishihara, just a second.
Yes.
If you can finish it within 5 minutes. We are running behind.
Okay, sorry.
Thank you.
Okay, sorry. So this is a substrate scope. This is also substrate scope. Okay, so this is also substrate scope. So this is our proposed transition state. So the lithium salt is here. So alkynyl lithium is coordinated to dilithium salt, and the charge relay to increase the nucleophilicity of phenylalkynyl moiety, and this lithium Lewis acidity also important for activation of carbonyl moiety. Cyclohexyl moiety insert alkyl macrocyclic cavity. Then, so this is a hydrophobic interaction between the alkyl chain and the cyclohexyl moiety. Then enantiomer selectivity was observed. Okay, so skip. So okay, I want to show you the last result. So just we mixed 3 different type of ketone. So in this case, if we use C16 ligand, so substrate selectivity, enantiomer selectivity are also observed, like an enzyme. Okay. So this is a summary. So main player is Professor Manabu Hatano. He is now Kobe Pharmaceutical University. So, and Dr. Kenji Yamashita, he is now the University of Shizuoka as assistant professor. Thank you for your kind attention.
Thank you, Professor Ishihara, for your exciting presentation. as we're running behind the schedule, probably one question we can take at the most. If the participants, they have any questions, can raise their hand using the raise button.
Pardon?
No, it's for the participants, those who are listening the lecture. Okay. For questions.
Okay, thank you.
Okay, there are no more questions. We thank Professor Ishihara for sparing valuable time with us and giving an excellent presentation. Thank you, Professor Ishihara.
Yes.
Over to Susan. Thank you. Thank you.
Thank you.
Yeah, thank you, Professor Ganguly, for chairing the session, and thank you, the speakers, for giving excellent lectures. So may I now request Professor P.S. Subramanian for giving chairing the session too.
Thank you, Dr. Shkulyan. And this Professor Santanu Mukherjee is known. The invited speaker, today's invited speaker, Professor Santanu Mukherjee, is well known to CSNCRI. Good morning.
Good morning.
Good morning. I don't think that he needs any introduction to CSNCRI people. The introduction is for only outsiders. Of course, those who are working in the core area of organic chemistry is know about Professor Mukherjee. Just for the sake of introduction, I am giving a short and brief introduction. Professor Santanu did his MSc in the year 2002 from IIT Kanpur, and then joined for Professor Albert Berkesel in the University of Kolin for his PhD in 2006. The interesting thing is that today's present session, the two speakers, they are from the Nobel Laureates group for their postdoc, and Professor Mukherjee has done his first postdoc with Professor Benjamin List in the year 2006 to 2008, followed in the group Dr. Professor E.J. Corey from Harvard University, the year 2008 to 10. And then he returned back to India and joined in IISc as an assistant professor. And subsequently, he got promoted to associate professor in the year 2015 and then 2021 as a full professor. Currently, he is working as a full professor in the chemistry department, Department of Organic Chemistry, IISc. He has received many awards. To name few, Theme Chemistry Journal Award in the year 2011 is one of the prestigious award. And then INSA Medal for Young Scientist in the year 2014. So the list really goes long. So thinking that to give more time to speaker, I'm cut-shorting it. And he is currently associate editor for Organic and Biomolecular Chemistry. He served as a member in the editorial board, Journal of Organic Chemistry. Currently, he is the member of SINLET Theme Advisory Board. With this short introduction, I'm giving this platform to Professor Mukherjee for his talk, Breaking Symmetry, Development and Application to Complex Targets. Professor Mukherjee is yours now, please.
Thank you so much. Am I audible?
Yes, audible. Okay. Please go ahead.
Thank you for a very generous introduction. I hope my slide is visible, right, in the full screen mode?
Yes.
Oh, okay. All right. So let me begin by thanking the organizer, particularly Sukalyan, for putting together this half-a-day fantastic program with some of our colleagues and role models, I would say, from Japan. I've seen Professor Ishihara, Professor Yujiro Hayashi will be the next speaker. So it is a privilege to be sharing some of our works on the same platform, and particularly since Professor Ishihara and Hayashi, both of them have done the postdoc in the same place where I have also done with Professor Koretz. So it's an interesting coincidence that we have it today here. So today I will talk about breaking symmetry, but before we go there, let me briefly tell you what our group has been working on. Just a second. Somehow my slide is not changing. Oh, now it's fine. Yeah. So our group is primarily working on asymmetric catalysis. And then there are various areas of asymmetric catalysis that we have been working on over the past 14 years in this institute. And our broad area of work has been based on organocatalysis. And we have seen a fantastic lecture by Professor Isiara's group just a few minutes ago. But in the last few years, we are also moving towards transition metal catalysis with an objective of exploring the exciting prospect that lies at the interface of organocatalysis and transition metal catalysis, or rather combining some of these aspects of both these powerful areas of catalysis to see whether some new reaction can be discovered. Now, since today's topic is breaking symmetry, let me give you very briefly, I'm sure the speakers don't need an introduction what is breaking symmetry, but for the sake of student audience, I'll just briefly tell you what do we mean by breaking symmetry. So if you think of a molecule of this type where we have two identical functional groups at the two end, then the intervening center is not yet a stereo center, because however, these two groups are so-called enantiotopic groups, because if you convert one of these groups to a different functional group, then this prochiral center gets converted to a stereo center. But if this reaction is not selective and the other group gets converted, we will of course get the enantiomeric product. Needless to mention that if both of them are converted at the same time, then we'll get the again the prochiral product. The same is also true for the meso compound, and we can, in this case, we can generate multiple stereo centers in the same operation. And this type of reactions are normally known as enantio group selective reactions, or in short, desymmetrization reactions. Now, there are multiple advantages of this type of chemistry because you can generate multiple simultaneous stereogenic centers through a single operation, and it is possible to create a stereo center distant from the reaction site, which is normally not the case for most enantioselective transformations that we often come across. Now, the question is, if we are thinking that we can create multiple stereogenic centers, so how far it can be from the reactive site, and we can still be able to control the reaction site. And most importantly, why even bother about breaking symmetry? So in the next 25 minutes or so, I'm going to try and give the answer of some of these questions. And hopefully I'll be able to convince you that breaking symmetry is indeed a very powerful strategy when it comes to making complex targets. Now, just to give you an example from our group on the first reaction that I talked about, the cartoon representation I talked about, you can think of this molecule as similar. We have the nitromethylene group, two identical nitromethylene groups, which are enantiotopics around this prochiral center, and they can be converted to a chiral compound by two different means, either stereoselective modification of the nitro group or modifying this methylene group next to the nitro group. So we chose the latter one, and with the use of a bifunctional thiourea, tertiary aminothiourea molecule of this type, we could do an organocatalytic allylic alkylation reaction of the nitroalkanes very selectively. And in this process, not only this center gets converted from a prochiral to a chiral center, we generate another additional stereo center at this position. So of course, we get the product with very high enantio and diastero selectivity. I'll not go to the details of these reactions, but today's topic will mostly focus on this reaction which we discovered about a decade ago. And this reaction is quite interesting because it's not only a desymmetrization reactions, but as I mentioned that in a desymmetrization, you can create a stereo center that can be away from the reaction site. So in this particular case, the CH group, so there are two CH groups which are enantiotopic. Now, one of them gets selectively converted to a CC bond, or we break a CH bond to form a CC bond, and using nitroalkane as the alkyl source in this reaction, which is not usual. And now, importantly, the reaction is happening at this site, but we are creating a stereo center that is two bonds away from the reaction site. So, and overall, we would like to call it a near ideal desymmetrization reaction because in this case, we are not creating any additional stereo center. We are not changing the functional group that are present in the molecule. We are simply desymmetrizing the molecule and generating a stereo center. And we can get this reaction to proceed with a very high enantio selectivity. Our initial mechanistic proposal was something like this, that in the presence of this similar tertiary aminourea derivative, the nitroalkane can do a enantiomer position selective conjugate addition through this type of a activation concept where the protonated tertiary amine can activate the Michael acceptor, and then the nitronate, the corresponding inlet from the nitroalkane, can actually do an enantiomer position selective conjugate addition reaction. Now, after the reaction is complete, this proton alpha to the carbon is quite acidic, so therefore it can eliminate nitrous acid and form an exocyclic double bond, which undergoes isomerization to the endocyclic double bond. Now, after discovering the initial reaction with cyclopentene dione, we went ahead and applied this to this meso quinone, and we can do it. Now this is a meso compound. The previous one was a prochiral compound. In this case also we can get the product with very high enantiomer selectivity, and this is quite interesting because this type of Diels-Alder adducts are not possible to make directly through a Diels-Alder reaction in an enantiomer selective manner. Not only that, in this reaction, so this is again the mechanistic proposal, we had the same one what I told earlier, and for one particular substrate along with the final product, we could actually isolate the Michael adduct with very high diastereomeric and enantiomer selectivity. And once after isolating and characterizing this compound, if we treat this with an achiral base, in this case potassium acetate and 18 crown 6, we can get the same product with the very same level of enantiomer selectivity. That shows that indeed the enantiomer position selective conjugate addition is the enantiomer determining step and the determining step of this process. Now, unfortunately, when it comes to cyclopentene dione, we could never detect or isolate this Michael adduct. So that brings us to the question about what is the mechanism of this reaction. More specifically, how does catalyst control the remote stereo induction, and what is the rate and enantiomer selectivity determining step? To answer this question, we thought of combining an experimental technique called natural abundance 13C kinetic isotope effect and the DFT calculations. And we have done that with the collaboration with Professor Jennifer Hirsch's group from Binghamton University. I will not take you to the whole details of this study because of the lack of time, but what we found in this case, it is not the enantiomer selective conjugate addition, but it is actually the elimination of the nitrous acid that is the rate and enantiomer determining step of this process. So which is significantly different from the quinone that I just talked about. And coming to the origin of enantiomer selectivity, we can look at the two diastereomeric transition state, and we can see that the calculated difference in energy between the two diastereomeric pathways actually corroborates pretty well with the experimental value of about 1.28 kcal per mole. In terms of E is like 94 versus 96% T, which is in good agreement. What we found quite interesting in this case that one of the key factors that contributes to the stability of the major pathway is a favorable CHF hydrogen bonding interaction, which is absent in the minor diastereomeric transition state. And to provide some evidence in support of this, if we change the trifluoromethyl group in the catalyst to the methyl group, we see a substantial drop in enantiomer selectivity. So which is also explaining that lack of CHF interaction with the dimethyl catalyst. Now, again, like I'll just quickly wrap this up. This study what we have completed a couple of years ago, that it is the nitro elimination by U1CB mechanism is the enantiomer determining step in this process. Now, while thinking of an application of this particular reaction, we became interested in this type of lateral phospholipids, which are isolated from the membrane of this bacteria called Anamox bacteria, that is anaerobic ammonium oxidation bacteria, which basically converts ammonium nitrite to the molecular nitrogen. And this reaction takes place inside this bacterial cell called anamoxosome, and which is of course surrounded by a couple of other compartments called riboplasm and periplasm. So while trying to figure out the role of this membrane from which this type of phospholipids were isolated, so what was discovered by Noah Burns and Stephen Boxell's group is that this membrane actually helps in maintaining a pH gradient. As you can see, inside anamoxosome, the pH is about 6.3, outside is 7.3. So therefore, what membrane does, it prevents the proton permeation across this membrane. Now, These are a couple of examples of these ladderin phospholipids. It's called 5,3-PC because this is consists of 5 ladderanoic acid with these 5 ladder-like arrangements of 4 concatenated cyclobutane ring. And in this case of a 3-ladderanol, we have 3 such cyclobutane rings are concatenated. Now, when it comes to the synthesis of these molecules, there are of course many reasons for the synthesis. I will not go into the details. If there is a time permits, we can discuss afterwards. And there are several syntheses that has been taken up, mostly by 3 groups. Professor Kore's group developed the first synthesis of 5-ladderanoic acid 2 years after the initial isolation of the compound, followed by an unselective synthesis of this compound, and then Kevin Brown and Noah Burns came into the picture, and they synthesized both 3-ladderanol and 5-ladderanoic acid. Now, quickly looking at their approaches, so the Burns approach basically relies on a kinetic resolution of this dibromodiol using a lipozyme with basically the esterase enzyme, and which was oxidized to the corresponding dibromo compound, and they did a 2+2 cycloaddition to form this core structure of the 3-ladderanol. Afterwards, they did an elimination, and then they used an alkyl zinc to couple to get the +3-ladderanol. Brown's approach was somewhat different. They did an organocatalytic energy-selective isomerization of the deconjugated iones to form the allenone, which they used for 2+2 cycloaddition using bismuth triplet in a chirality transfer 2+2 cycloaddition. And afterwards, they actually coupled with the same type of alkyl zinc complex, this long chain was attached here, and which was eventually taken to the product. So the commonality between these two syntheses is that the long chain alkyl group or the stereocenter was established at the early stage of the synthesis. So our approach was something else. We thought this type of compounds can in principle be prepared by cutting this or clipping this CC bond and through the breaking of the symmetry, because now we have this 5-ladderan and 3-ladderan moieties, which are meso compound. And if you can stitch this CC bond, we can actually get to 5-ladderanoic acid and +3-ladderanol. Now, it is of course easy to tell because these compounds do not contain any functional group in the core structure. Of course, I'm not counting the alcohol because the reaction is happening at a site where there is no other functional group. So this is an extremely challenging CsP3H, CsP3H coupling. So we thought of introducing some clip in the form of functional group, which will allow us to clip this bond and bring us to this meso indione and a long chain alkyl, particularly the nitroalkane group, to apply our reaction for this enhancer selective desymmetrizing CsP2H alkylation reaction. Now, there has been a couple of challenges at the beginning that we could recognize. One is that on the drawing board, the previous reactions, whatever we have talked about, like particularly with an indione, it relies on the inertia of position selective conjugate addition for the 6-member ring. 5-member ring is the elimination of the nitrous acid. However, if we look closely at the substrate, all the substrate, then we can see that the substituents are actually pretty close to the reaction site. Unlike in the transfused cyclobutane rings or in the 3-ladderanol, where the substituents are actually trans to this side, so they are quite far from that. So we are not sure whether our catalyst will be able to discriminate between these two positions of this cyclohexene diene. Second problem was how to actually prepare this one. So when it comes to the first problem, so we thought let's tackle this by using a simplified model substrate. So instead of a cyclobutane, if you can have a cyclopropane here, it's much easier to synthesize in 2-3 steps with a literature reported method by Professor Deepak Mali in IIT Kharagpur. We could make this in good yield, and Sion, my student, he was actually working on that, and he single-handedly developed and optimize these reactions. I'm not taking you through the entire optimization. Now, this is a tertiary amino squaramide catalyst, which leads to the product with decent level of enhancer selectivity. So now getting enough confidence on this type of, that our reaction can in principle be applicable for this type of substrate, we came to the synthesis of this compound. And this took us significantly amount of time. Because if you think of general synthetic strategies for ladderins, one of the simplest would be to clip this ladderin in vertically or rather horizontally, and that brings to these two polyene scaffold, which can in principle be cyclized with a series of 2+2 cycloaddition. But that requires not only the parallel alignment of this polyolefin unit, but the separation between the two olefins has to be perfect so that the reaction takes place under photochemical condition. And that was shown. This is of course entropically highly unfavorable unless you pay the entropic penalty at the very beginning and attach this chain to a kind of a rigid backbone like paracyclophane, and now these chains are pretty close to each other, so therefore photochemical 2+2 cycloaddition can take place. But when it comes to the synthesis of laterales, there has been quite a few methods. The first one was developed by Meinwald in 1974, where they took advantage of this anti-aromaticity of cyclobutadiene to do a double 4+2 cycloaddition under thermal condition to get the stereodactyl imodines, named after these flying dinosaurs. Professor Mehta's group took this strategy and applied to functionalize cyclobutadiene, and they could get up to 13 laterales, and they have done detailed study and energetics of this type of reactions. But we became interested in this report by Martin et al. In 1981, where they do a systematic analysis of 2+2 cycloaddition and Rambach-Backlund reaction, and that gives a systematic opportunity to prepare any type of laterale. I will show that in a few minutes. Now, for that, the first reaction requires, in our case, a 2+2 cycloaddition between malic anhydride and methylene. And this reaction, it took several months for us to establish, and this is the final setup. And we must thank Professor N.D. Pradeep Singh from IIT Kharagpur to help us setting up this photoreactor in our lab. And Sion could eventually do this reaction in a very large scale, about 250 gram scale approximately, and then we can reduce that to the corresponding diol. So both the diol and the corresponding acid are commercially available, but you can see the price of this diacid. It is extremely expensive. The alcohol is even more expensive. So therefore, we decided to prepare it and then take it forward. So we can protect the OH with a methyl group and then replace with the sulfide to get this bicyclic compound. So the first 2+2 cycloaddition established the first 4-membered ring. And then afterwards, we oxidized with the corresponding sulfoxide, made an alpha chlorosulfoxide, and then performed a Rambach-Backlund reaction to form this so-called 2-laterine or bicyclic hexene or cyclohexene. And so once we have this, we could not purify. This is really volatile. We took it forward and did a 2+2 with the cyclohexene dione, and we can do we can get the meso compound, which was our desired one after another oxidation of this part with selenium dioxide. Now, having synthesized that one, this part, now we decided to couple with the entire long carbon chain at this stage, where we will be also doing this reaction enhancer selectively. So in the single operation with the bifunctional catalyst, you have to use an achiral catalyst to facilitate the elimination. That's a long story again. But in the single operation, we can set up the entire skeleton along with the right stereochemistry in almost all carbon except this one in the single operation through the desymmetrization reaction. Now, we had to remove the functional group. So the first we did the formation of the hydrazone. This is following Noah-Burns procedure using copper timidamide denitrogenation to get this diene, which under Crabtree's catalyst hydrogenation condition provided the product with the right stereochemistry, and then elimination of the or the deprotection of the TBS group gave us 3-laterine node. If we couple with an isocyanate, we can actually get the final product. Cyan got the extra structure of this compound, and which establishes the absolute configuration and beautifully shows the ladder-like arrangements of this 6444 unit in this position. This is something that we published in 2022. Now, of course, the key features of our strategy was the late stage enhancer induction. After this, we have only 3-4 steps to go to the final compound, and which could allow the efficient access to other analogs and the enantiomer of lateral. Having done that, we thought, let's focus on 5-lateronic acid. Now, as I mentioned, the first report was by Kore in 2004, and it's a step-by-step approach to the racemic compound. And afterwards, Kore applied a chiral starting material or the starting cyclopentenone for 2+2 cycloaddition reaction. They basically desymmetrize 3-laterin unit to build the final 5-lateronic acid. Burns actually use a 5-laterin unit for the desymmetrization through energy selective hydroboration reaction, and then they coupled it with this under Zweifel olefination condition and followed by a couple of steps to get the 5-lateronic acid. Brown reported, on the other hand, 4-laterin. So from Core's case it was 3, Burns' case it was 5, and then Brown's case it was 4-laterin, and then did a carboboronation reaction for the desymmetrization reaction, and then they went ahead to establish there's quite a bit of steps, and it's a fairly long synthesis. And so now the question is, if there is already so many syntheses reported, why do we want to make another synthesis? Now, for that, we have to go back to the carbon skeleton that is common for both 3-laterinol and 5-lateronic acid. Now, I have put some dotted bonds here because if you systematically, or if we keep all the bonds intact, that gives the 5-lateronic acid. But if you clip one after another systematically, and that gives the other possible products. Now, this is 3-laterinol. So these two are the natural products. Now we ask the question, what about the other 3? Are they natural product that has not been isolated yet, or nature perhaps made it and chose to not to continue in the process of evolution, and so therefore they are not natural product because for the purpose it was supposed to act and it has not been functional. So only way to do that, if we can make all of them, and then we can see how permeable proton is consisting of the membrane of each of them. So for that, we need to have a unified strategy to synthesize all of them. We have already synthesized 3-laterinol, so we need to synthesize 5-lateronic acid and other 3 unnatural compounds, the quote-unquote unnatural compounds. Now, the common feature of this is that the long chain is attached to the cyclobutane ring, which is different from 3-laterinol, where it was attached to the 6-membered ring. So therefore, we could do a desymmetrization of the meso-indione. And we have seen the desymmetrization of the meso-indione for 6-membered and 5-membered case. But obviously, we cannot have a meso-indione on a 4-membered skeleton. So therefore, this desymmetrization directly will not be applicable in this case. However, it can be applicable if you put a 6-membered ring here temporarily, and we can attach this ring here. So the previous strategy I have discussed. What we need to do, so this is of course a reaction that I have already mentioned. And what we need to do is the deletion of the 6-membered ring, which will bring this long chain here. And that can be a common method for 5-lateronic acid and other possible laterin units in this case. So this is just put a cartoon representation for the easy visibility here. So this is the common feature of all the natural and unnatural compounds I talked about. Now, we need 2 strategies. So one is the symmetry breaking alkylation reaction that we are confident that it is going to work. And the second would be the breaking of the 6-membered ring. So the possible deconstruction strategies. So there are a few ways it can be done. One is a 2-carbon deletion, and that can bring this diketone, which can be deoxygenated to give this final product. Second possibility would be a 3-carbon deletion to get this ketone, again deoxygenation to get the final long chain alkene. Third possibility is a single carbon deletion approach that will give a different compound, and we need to do a deoxygenation and hydrogenation to get the compound. But now, unlike these two, this is actually giving a difference. So unlike the 2 and 3 carbon deletion approach, the single carbon deletion brings the opposite enantiomer. So therefore, we need to use the enantiomeric catalyst for the symmetry breaking operation. More importantly, depending on whether we are deleting 1, 2, or 3 carbon, the long chain has to be chosen accordingly. Now, so we know that this is generally works. So we thought of focusing on the deconstructing carbon deletion approach, and we chose to use this type of model substrate because this is easy to prepare and it can be obtained in a good EE as well. So our initial 3-carbon deletion strategy was to do an ozonolytic cleavage of this double bond to get the ketoaldehyde, and then followed by the decarbonylation using Wilkinson catalyst and to get this product. When we actually tried the reaction under ozonolytic condition, this worked, but by addition of one water molecule, it kind of cyclized to give a very complex acetal and hemiacetal species, which we thought might be in equilibrium with this ketoaldehyde. So I thought, let's try the decarbonylation reaction, but it didn't work. ozonolysis on a different condition could give us this diketo here and cleavage of one of the carbon and give the carboxylic acid. So we thought if you can do the decarboxylation reaction here, that can give us the desired compound as well. However, this two carbon deletion approach over several steps, it actually did not work. We actually got a different compound. There are many other things we tried. I will not go through that, but all these attempts actually failed for the 2 and 3 carbon deletion. So we thought, let's try the single carbon deletion approach. So for that, we need to have distinct steps. One is the chemoselection deoxygenation reaction, followed by the cleavage of the CC bond, and finally the 1 carbon deletion either by decarboxylation or decarbonylation reaction. So initially, when we focused on the chemoselection deoxygenation reaction, and my student Sion developed a beautiful reaction after initially doing the Lucid reduction. He could treat it with BF3 etherate, and it does a vinyl locus pinnacle rearrangement, possibly through a selective coordination to this less hindered alcohol, and that gives single diastone of this product. Double bond is in the wrong position, but that's not a problem because by doing this reaction at a for a longer time can actually isomerize this, and we can get the chemoselective deoxygenation. Now what we need is the CC bond scission reaction. For that, we had to initially hydrogenate the double bond. We have the ketone, we reduced it after the mom protection, and then elimination by methylation gives this olefin. We can cleave this one now, and that gives us the ketoaldehyde. Although the decarbonylation did not work, we can actually do the oxidative ozonolysis here, and then followed by decarboxylation that took us to the final compound. Now all is required is the deoxygenation reaction, which we can do through the modified Wolff-Kishner condition. Now this is the overall route from this 646 to this final compound. And with the model system, there are total 11 steps, but only 4 chromatographic purification, and we have 11% overall yield. So having done this deconstructive carbon deletion approach, we next had to focus on preparing this meso compound for the before the 2+2. I've already talked about preparing this one, this bicyclic compound, and which we can do a 2+2 with the cyclopentenone and to form the third 4-membered ring, and then alpha diazo Wolff rearrangement to get the 4th 4-membered ring, and then the decarboxylative bromination give the bromo compound here. We can eliminate to give the 4-laterin. Now, having done the 4-laterin, we had to do a 2+2 cycloids from the cyclohexene dione to form the 5th 4-membered cyclobutane ring here, and then selenium dioxide gave us our initial meso compound, which we need to desymmetrize. And now, having done that, we did the desymmetrization reaction under the same condition or very similar condition that we had before. This time we can use the DAPCO instead of the chiral bifunctional catalyst, and that gave the final product with 78%. Now the end game, I'm not taking you through the entire thing, but it's the same as the model substrate. In total 11 steps from this, we can get to 5-laterinol, and then oxidation with Jones oxidation took us to the 5-lateronic acid in 82% yield. So the overall strategy requires total 11 steps again, 6.4% yield and 4 chromatographic purification, and but you can get the 5-lateronic acid. And this is actually optical rotation as well as the proton and 13 CNMR matches well with the previous report by Barnes group. Now, so this is what we set out to do, an unified strategy to make them all. We could come up with a unified strategy, made 5-lateronic acid. We could also take it to the inverse 3-laterinol as we call. So out of these 3, the 2 are already done. So these 2 we are currently working on. So hopefully once we have them, we will be able to come up with a possible biosynthetic logic by nature, and hopefully we'll be able to answer some of these unanswered questions. So what I told you today, the application of our CH alkylation, desymmetrizing CH alkylation reaction for 3-laterinol and also for 5-lateronic acid and other unnatural analogs. Now, I began by asking a few questions like how far the stereochemistry can be controlled and why do you even break symmetry. So I hope I was able to give you an answer to some of these questions and show you that desymmetrization can indeed be a powerful strategy for breaking symmetry. The major credit for this work goes to my student Simon Ray. First day when he joined the lab, I told him we want to apply our reaction for the synthesis of this type of ionic phospholipid, and he took the challenge and he almost single-handedly developed the strategies for the entire thing. And in terms of experimental work, Suvajit helped him in the 3-lateral project. Prabha is currently working on 2 other unnatural compounds. And of course, the initial developments were done by my first student, Madhusudan Manna, and Rahul Sarkar, and Deepak Behra was a project assistant in between. He helped Simon with some of the experimental work. So this was my group from last year. There are a few new members after this. And I must thank all the funding agencies for supporting our research, particularly ACRB, and our collaborators, Jennifer and Garima, my colleague, for helping us understand the mechanism of some of our reactions. And I must thank you for your attention, and thank you again for inviting me for this one-day webinar. And I'll be happy to answer if you have any questions.
Okay. He's already on. You can talk.
Yes, the dais is open now. If there is any questions, 1 or 2 may be allowed.
Yeah, I have a one question.
Yes.
Yeah. What is the physical state of ladderonic acid?
It's a solid compound. It's a solid compound.
And what is the solubility of this compound?
It is soluble. We have done the NMR and CDCl3, but I think it is generally soluble in most organic solvents. So including methanol and other solvents as well.
Is there any thought on making a kind of a what do you call membrane architecture using these kind of what do you call synthetic stuffs?
Yes, we are. We are currently so we are collaborating with. I think okay. There was a different story also. We have been trying to make some other types of unnatural ladderant by inserting a benzene ring there. So we have completed that work. I did not talk about it today. So we have prepared some of the membranes using that so-called benzoladderin, and we compared the benzoladerinol with the laderinol natural one by making some membrane by doping them, and then to see the proton permeability across the barrier. And we found the benzo one to be more impermeable. So we are trying to do some more studies on that. But this one, once we make all 4 of them, yes, we do have a plan to generate the membrane or produce the membrane using this type of molecules and see how they affect the proton permeation and the permeation of other molecules across the barrier. So this type of compounds can have a lot of other applications as well as a drug delivery vehicle and so on.
Sorry. Thank you.
Thank you, Professor Mukherjee. You are very much well within the time. So you have, I think, since we are nearing the lunch time, you have finished your talk so nicely. Exciting talk. Thank you. Thank you very much.
Thank you.
Let us go to the next speaker, Professor Yujiro Hayashaki. Good afternoon. Good afternoon.
Good afternoon.
Yeah. We welcome you on behalf of this webinar. Professor, to introduce Professor Hayashi, he is currently professor, the Department of Chemistry, Graduate School of Science, Tohoku University, Japan. And then with his educational background, he has done his BS in University of Tokyo at the year 1984 under the research advisor, Professor Teruki Mukayama. And then in 1992, he completed his PhD at the University of Tokyo under the guidance of Professor Koichi Narasaki. And then 94 to 96, as I mentioned, it is the session of Professor Kore. He worked with Professor Kore during this 94 to 96. So then he joined in 87 to 98 as assistant professor in University of Tokyo, and 98 to 2006 associate professor, and then subsequently promoted to professor the year 2006, and then from 2012 to now, continuing as a full professor in the same Tohoku University Graduate School of Science. He has many awards to mention. Since we are running with the now some time short, so I'm just naming little. 1998 Incentive Award in Synthetic Organic Chemistry, and then in the year 2010 Chemical Society of Japan Award for Creative Work, and then in 2011 JSPS Award for Excellence, and in 2011 Novartis Chemistry Lectureship Award. It seems that for his outstanding contribution on organic chemistry, including biology, which is now given in the year 2011, and then Applauser Award, and 2012 Prize for Science, and 2024 Ikimura Prize for Science for Excellent Achievements. He is basically working on organic synthesis, development of new synthetic methods using organocatalysis, synthesis of biologically active natural products. So with this short introduction, I request Professor Yujiro Hayashi for his talk on ecnochemical synthesis of biologically active molecules using organocatalyst. Professor Yujiro, that is yours now.
Thank you very much, Chairperson, for the kind introduction. And first of all, I'd like to thank you from Professor Batra for the kind invitation this special symposium for catalysis. So for synthesize the target molecules, the important thing is the reaction and catalysis, which we are now discussing, and also strategy. So as for catalysis, my group has interest in organocatalysis because there are several methods such as metal waste is not generated, no metal residue in the product, and stable in water and oxygen and so on, and safe and secure catalyst, and inexpensive. Because of these reasons, our group developed this catalyst that is now called Hayashi-Jorgensen catalyst. And for synthesis strategy, my group has interest to do several reactions in one pot, and we propose the pot economy. First, I'd like to talk about the catalysis. So all of you know that 2001 for H-met catalysis, for metal catalysis, Nobel Prize awarded to these big figures, and 2021 Nobel Prize awarded to organocatalysis, and Macmillan or Rist and Macmillan received ours. Rist reported that fluorine is a suitable catalyst for aldol reaction in which ketone and fluorine react and enamine forms, and this proton is important. This proton activates the aldehyde. In that case, this aldehyde coming from the same side of this carboxylic acid moiety, then he obtained a high excellent enantiomer selectivity. And Macmillan developed this catalyst, so-called Macmillan's catalyst. In his case, alpha beta unsaturated aldehyde reacts with amine, and that iminium ion forms, and this is a highly electron withdrawing group, so that this double bond is highly activated. And using this Macmillan's catalyst, he obtained a high enantiomer selectivity in these other reactions. Our group developed several reactions using fluorine as a catalyst. And also we developed siloxyfluorine. This is a suitable catalyst for aldol reaction in the presence of water. And we also developed CF3 substituted diallyl fluorinol, which is a suitable catalyst for cross-aldol reaction between two different aldehydes. And today I'd like to talk about this catalyst. What is an effective asymmetric catalyst? Excellent enantiomer selectivity, high reactivity, easy preparation, wide generality. So according to researchers, probably the criteria might be different. And each researcher would like to make his or her own catalyst. But today I'd like to emphasize that important thing is what reaction would you like to develop? So I'm interested in reactions, aldehyde nitric alkane reactions, because I saw that the products should be very important for natural product or drug synthesis, which later I will show you the example. When I started this project, 2002, there's no asymmetrics, there's no asymmetric reaction with excellent enantiomer selectivity. So 1980, Zeebacher reported that equimolar amount of enamine react nitrostyrene to afford a molecule product. And these errors, nobody saw that catalytic amount amine can promote these reactions. The first person to make this reaction catalytic is Burbus. He developed this amine catalyst and obtained moderate yield. And Alexis reported this catalyst and 85% yield. I thought this is a very important reaction, then I like to improve the enantiomer selectivity. Then I started to investigate the catalyst. Our approach is try and error approach. So in that case, we have several catalysts, mostly chlorine-based catalysts. And we are happy to find that this diphenylprolinol is highly enantiomer selective. But the problem is that reactivity. Even in the presence of 20 more % catalyst one day, yield is not good. We check the solvent so on, but reactivity does not increase. At that time, we had the following result. This is the alpha aminoxylation of ketone with nitrobenzene, and pro is a suitable catalyst. And at the time, we found that siloxyproline, which is developed for the aldol reaction, is a very nice catalyst. Much shorter time, reaction finished. So introduction of siloxy group to catalyst, then the activity of catalyst increased. So we have some problem in this catalyst. In that case, I just asked my student, why don't you silylate this? And he made silylated catalyst. And we are very happy that the catalyst reactivity improved. Half amount of catalyst, only 5 hours, 85% yield, good diastereo, and excellent enantiomer selectivity. That was 2005. Now, at the same time, Jorgensen's group reported that trifluorosubstitute diaryl similar catalyst also act as a suitable catalyst for aldehyde alpha functionalization. So after this, our group and Jorgensen's group are competing. And right now, many people use this type of catalyst. As for this particular reaction, after 6 years afterwards, we found that in the presence of paranitrophenol, the reactivity of catalyst improved, and only 1 more % of the catalyst, much shorter time, much higher yield, much higher syn selectivity, we obtain this product. So this is a reaction mechanism. Catalyst reacts with aldehyde and enamine forms. When this is OH is free, in that case, this is the equilibrium with N-acetal. In that case, concentration of enamine is low, so that the reactivity is low. But by silylation, the concentration of enamine is high, so that reactivity increased. So then without in the presence molecular sieves, we mixed enamine and nitroalkane. In that case, we observed this cyclobutane, these 6 membrane compounds. And when we add acid, these 2 compounds, catalysts are trapped. So there are no catalysts in the reaction cycle. But when we add acid, these 2 compounds converted to molecule product. So the effect of acid is to return this intermediate to the reaction cycle. So we found this catalyst, and this reaction proceeds highly diastereoal enantiomer selective manner. And my catalyst reacts with aldehyde and enamine forms. And in this case, this moiety covers 1 enantiomer phase completely, so we can functionalize alpha position of aldehyde. And this is the X-ray, and this moiety covers 1 enantiomer phase, and this moiety is completely open. That's why we have an excellent enantiomer selectivity. And this catalyst also reacts with alpha beta unsaturated aldehyde. In that case, ion forms, and also it covers 1 phase. And in this case, we can functionalize the beta positions. So I'd like to explain the difference between the chlorine and Macmillan's catalyst. In the case of chlorine, as I told you, this proton is very important to activate the electrophile. But according to the electrophile, this bond length should be different. So suitable electrophile are rather limited, such as aldehyde, imine, and some of the molecule acceptor. But in our case, this moiety completely covers. So electrophile coming to the opposite side. So as far as the reaction does proceed, in both cases, we obtain excellent enantiomer selectivity. And in the case of Macmillan's catalyst, this is very good for iminium ion, but is not so good for enamine as a catalyst. So our catalyst has a suitable nucleophilicity as enamine and also suitable electrophilicity as iminium ions. And this is a secondary amine. Secondary amine is not so basic, and also this is a bulky substituent. That's why this amine catalyst is not basic. So it does not affect other reactions. But this catalyst activates aldehyde and alpha beta unsaturated aldehyde pinpointedly. That's why this catalyst does not affect other reactions, and we can use this catalyst in one-pot reactions, which I will show you later. So these are products synthesized by this simple catalyst. This result from our own laboratory, and Jorgensen's group and other group all over the world now utilize this catalyst. And this catalyst right now, one of the most used catalysts. So there are several terminologies such as atom economy proposed Trost and step economy proposed Bender and redox economy proposed Baran and Hoffman. And I propose pot economy. To perform several reactions in one pot, it can improve yield, it can save time, and also it can reduce waste. So pot economy is very important. Also pot economy is important for green reactions, green chemistry. So in my group, we synthesize Tamiflu in one pot within 60 minutes. And also prostaglandins, E1 methyl ester, we synthesize 3 pots, and then steroid, estradiol ether, we synthesize 5 pots. Today, then as for the importance of one pot, I wrote this perspective, pot economy and one pot synthesis. How pot economy is important, please read this paper. So today's molecule I'd like to explain is latanoprost. Latanoprost is a treatment drug for glaucoma, and it is a blockbuster drug. Many professors, many research groups synthesize these molecules. And this is a Pfizer synthesis. Using these reactions, they synthesize corylactone. It takes 10 steps. And using corylactone, another 14 steps. They synthesize the latanoprost. So total 24 steps. And Agarwal recently reported latanoprost synthesis by using organocatalyst. So squishing aldehyde and proline and aldol reaction, he made bicyclic compounds with excellent enantiomer selectivity. And another 7 step, he synthesized the latanoprost. So total 8 steps, very short. But the problem is, this reaction is highly enantiomer selective, but yield is not so good. So this is our idea. As I told you, aldehyde nitroalkanes reactions should be very important. I like to use that method. So aldehyde nitroalkane methyl ketone here. In that case, microreaction occurs. In that case, this keto aldehyde would be formed. Then intramolecular aldol reaction occurs, and this is NO2 here. So E1CB elimination, we introduce this methylene group here. So these kind of compounds are important for PG synthesis, as shown here. Stoke and Isobe already reported that using this intermediate, they synthesize prostaglandins. So I like to make these compounds. So how to make this aldehyde? This aldehyde can be synthesized as follows. Alcohol and microcrystalline annihilation. Then we obtain the chiral alcohol. And from here, we enter one-pot reactions. So olefin metathesis with acrylane. Without purification in the same pot, we add TBS triflate, alcohol protection. In the same pot, we add hydrogenation. Then reduction occurs. Then we obtain these compounds. Only 2 steps and excellent enantiomer selectivity, we obtain this aldehyde. Next, we try this reaction using the model aldehyde. So aldehydes, this aldehyde and nitroalkane, the reaction does proceed, but this is rather unstable. And we try the intramolecular aldol reactions under basic conditions. Under many different conditions, we try these reactions, but we do not obtain the product, only complex mixture, because there are two electrophilic moieties, and also there is several acidic protons. So basic conditions, we cannot control these reactions. Then how to transfer this reaction? We'd like to do this reaction, not to basic conditions, but acidic conditions. So Mukayama aldol reactions. So our idea is that if we can make this still ether, in that case, acid aldol reaction occurs. In that case, we might have a chance to obtain the product. In that case, we have to use this nitroalkane. Here, this silino ether moiety is electron rich, so reactivity of double bond might be reduced. And in this case, 1,4 addition and 1,6 addition, there are two reaction possibilities. But anyway, we try this reaction using the real system. Using real system in the presence of my catalyst, we are very happy that reaction does proceed. And in this case, we can isolate the product. This is not unstable at all. And under a lot of Lewis acid conditions, we investigated a lot of Lewis acid and found that dimethyl aluminum chloride is the best Lewis acid, and we obtained the product. But this is not unstable, so we treat with this under this condition, and E1CB elimination occurs, and we isolate this compound. We are very happy that the desired compound obtained 74% yield, good yield, and also nearly optical pure. So these compounds, 1 and 1 prime here. So this stereochemistry opposite, only small amount, and both stereochemistry opposite, 1, 2 prime, double prime, also small amount. So highly diaselective manner, we obtain the product. And at the same time, we obtain the free OH. And in that case, diastereoselectivity, this and this position opposite is 3 to 1. And these two positions is opposite, 80 to 20. So very bad though. So why this kind of thing happens? Okay, in this case, these two isomer diastereoselectivity is 93 to 7. And we use this, and aluminum Lewis acid, in that case, these whole isomer would be formed. But this is high than just diastereoselective, this is low. So in the deprotection stage, kinetic resolution occurs, meaning that these three compounds, deprotection is rather fast, but this is slow. So because of that, we obtained this with high diastereoselectivity and other isomers converted alcohol. Why this deprotection is slow? We do not know exactly, but conformation is different, so that in this case, this distillation should be slow. So we obtained products. So by reaching 1,4 additional reactions, here we enter one-pot reaction, that is cis-selective olefin metathesis using this catalyst. Without, in the same reaction pot, we add reducing reagents, stereoselective reduction, and with acid treatment, the protection, all 3 steps proceed in one pot, then we obtain Latin frost. So starting from multi-crystal relations and our catalyst, Michael reaction, and intramolecular aldol reactions, highly diastereoselective, and by reaching 1,4 addition, then next 3 reaction, 1 pot reaction, then obtained lateral frost. Total 11 steps and 6 pots, and optical pure compound obtained. So this is the shortest pot synthesis of lateral frost. So this is the cover picture. So only 3 pot, intermediate here, and optical pure compound is obtained. And in this reaction, my catalyst is the key. So I explained this reaction, aldehyde nitroalkanes molecule reactions. And we also thought as follows. We also have following reactions. Ketone is a good molecule donor in the place of my catalyst. In that case, obtain these molecule products with high energy selectivity. And our idea is that this is the methyl ketone, and this is alpha beta unsaturated aldehyde. Previously, aldehyde and enamine forms, but here alpha beta unsaturated aldehyde and iminium forms, and the methyl ketone react. Okay, the difference is here, this is the nitro compounds, this is a ester. So it's very similar compounds, but this is the enamine chemistry, but this is the iminium ion chemistry. And our idea is that iminium ion, the methyl ketones attack it. And in that case, this is the enamine forms. And next intramolecular molecule reaction, then we can obtain this cyclopentanone, substituted cyclopentanone. So this reaction proceeds pretty well. We obtain this only single isomer and also excellent energy selectivity. So this is the process called is synthesis of a corylactone using Carlisle-Lewis acid. These are the reactions, the key step, and several reactions, highly diacetyl selective, and he synthesized corylactone. How about the reaction time? 5 hours, 8 hours, 10 hours, 10 hours, 2 hours. The time is not written. 12 hours, 1 hour, time is not written. So total 48 hours and unreported time for 3 steps. But this is a nice robust method, but it takes 40 hours and several steps. So I'd like to make corylactone by our method. As I told you, I developed these reactions so that from here, we make lactone and we convert this moiety by OH, by Tamao-Fleming oxidation. So this is my idea. So we try this reaction. First reaction, we already explained. So 5 mole %, 8 hours, 10 mole % catalyst, 1 hour. Both cases, single isomer and electrochemical pure compound obtained. Next is the reduction of aldehyde and stereoselective reduction of ketone. Because of increased stereoselectivity, we have to use bulky reducing reagents. Then ammonium chloride, we obtain diol in good yield, and acid treatment, lactonization, and obtain good yield. And the next treatment with HBA4 dichloroethane 80 degrees 4 hours, silicon phenyl bond is converted silicon fluoride bond. And this is rather unstable, immediately treated with H2O2 KF. In that case, carbon silicon bond converted carbon OH bond. So 5-step, 5-pot, 58%, not so bad. So I asked my student to optimize this reaction in terms of pot and also in terms of time. So this is the final results. First reaction, we used 10 mole % of catalyst. In that case, the reaction was completed within 1 hour. In the same reaction vessel, we add the reducing reagents, same amount. Previously, we do the reaction room temperature 1 hour. But we found that 60 degrees reaction finished within 15 minutes without decreasing the diacetyl selectivity. So reaction is short time because of higher temperature. Next, we use ammonium chloride, HCl, and HBA4 3 acid. So we use the strongest acid, HBA4, same amount. And in that case, protonation occurs and destroy the remaining reducing reagents, and lactonization occurs. That occurs within 1 minute. And previously, this reaction is THF, and this reaction dichloroethane. So we have to change the solvent. So my students do evaporate the reaction at 80 degrees. In that case, previously, it takes 4 hours, but right now, under the evaporation 80 degrees, the reaction completed within 15 minutes. So reaction became very fast. So this is because concentrate conditions, reaction was facilitated. After neutralization, we add H2O2, KF, and 1 hour, we obtained corylactone. So one pot, total is 50%. Then how about the reaction time? 1 hour, 15 minutes, 1 minute, 15 minutes, 1 minute, and 1 hour. So total 152 minutes, we can synthesize the corylactone. So when I talk with this, in that case, we all asked, you do several reactions in one pot. In that case, several byproducts should be contaminated so that purification might be difficult. But in this particular case, it is not. This is the NMR after the purification. This is the NMR before the purification, crude NMR. So several aromatic products involved, but as you can see here, this region have a good resemblance, not so much byproducts are generated. Why this reaction, crude NMR is also okay? I will explain. So this is a 5-step synthesis and total yield 50%, so meaning that each step, we use para-nitrophenol, but this also goes to water phase by acid-base washing. And we use this 1.2 equivalent, a little bit excess amount, but even though this remains, under these reaction conditions, this should convert here, and also this goes to water phase. So that's the reason that even though we do several reactions in one pot, purification is very easy. So there are several terminology, atom economy, step economy, redox economy, and as I told you, I propose pot economy. But from this result, I propose time economy. To make a single reaction fast is not good enough. It is necessary to make several reactions fast, and it is necessary to think about the purification of its reaction. So it is very difficult to make compounds in a short amount of time. So this is a guide toward the rapid multi-step synthesis of molecules. When you consider the reaction method, number one, employ rapid reaction frequent possible. I think all of you agree with this. 2, employ reactions that are easy to handle and fast to purify. And 3, employ domino cascade tandem reaction. So tandem and cascade reaction is an effective method to make a complex molecule. And when you think about the reaction scheme, meaning that retrosynthesis. Number 4, design the synthesis based on step economy and redox economy. Small number of steps in that case, reaction is much faster. And consideration of optimal condition in one pot. 5, find reaction condition under which the reaction can proceed rapidly. In our previous case, we used high temperature and concentrated condition. In that case, those reactions are facilitated. And 6, design the synthesis based on pot economy. In my case, we can skip the purification. In that case, total reaction time is shorter. Is making a molecule short amount of time important? So save time. If you make a molecule quickly, we can examine the function of the molecule. So unstable molecule is absolutely necessary. Rapid synthesis absolutely necessary. And PET synthesis. For instance, half time of carbon 11, 20 minutes, nitrogen 13, 10 minutes, oxygen 15, 2 minutes, fluoride 18, 110 minutes. In the case of carbon 11, isotope production 10 minutes and radio tracer synthesis and purification 40 minutes and PET imaging up to 90 minutes. Within this time frame, synthesis have to be finished. So rapid synthesis is absolutely necessary. So for production process, rapid reactions save labor costs and save energy costs and save equipment costs. We can use expensive equipment more frequently. And also, on demand, since it's possible, we can make molecules when and where we need them, and there's no need to stockpile the molecules. That's why I propose time economy. So I wrote this article. In here, I wrote importance time economy. And here, in this age of flu-based pandemics, the need for the provision rapid provision of effective therapeutic agents makes the importance of time economy particularly clear. It is our chemist's duty to make compounds fast, to make drug fast. And in the case of Tamiflu, previous synthesis over 37 hours, but my synthesis within 60 minutes. The Corylactone, previous synthesis over 48 hours, but my synthesis 152 minutes. And this is not my method, but ibuprofen is a drug. Batch synthesis takes 60 hours, but using flow, residence time is only 3 minutes. By using these three as a model study, we wrote this perspective. So this is 2021's first page. Then I wrote my idea about the time economy. So if you have interest, please read this. So today I talk about diphenylproinol silyl ether as an effective organ catalyst. And using this organ catalyst, I synthesize 6-pot synthesis of blatanoprost and 1-pot and 52-minute synthesis of corylactone. And this is the cover picture. Previous Tamiflu synthesis 37, but right now 60. Corylactone previously 48, 2.5. And this synthesis, important thing is this catalyst. And ibuprofen's case the same. And time economy is important. So that is the message. So this is my current group members. We are very happy. I'm very happy to work with these kind of talented students. And I'd like to thank you for your kind attention. Thank you very much.
Thank you, Professor Bayashi.
Hi.
It was really a very, very excellent lecture, and hope that you will still try to reduce multi-part reactions into single part. Your journey will be successful.
Thank you very
Successfully
much.
continue. Thank you, thank you. If there is any one question, since we are running with the shortage of time, one question may be allowed. Anyone? If there is no any question, I think we can go to the next session. Over to.
Thank you very much.
Thank you, Professor Hayashi.
Thank you. Thank you very much.
Okay. Thank you, Dr. Subramanian, for chairing the session. We will go to the next session, which is the last session of this webinar. May I request Dr. S. Adimurthy, Chief Scientist and of CSMCRI, to chair the last session.
Yeah. Okay. Thank you, Sukalyan. And this section we have two lectures. The first lecture is by Professor Biplab Maji. About Professor Maji is Associate Professor at present at Chemistry Department of Chemical Sciences at Indian Institute of Science Education Research at Kolkata. And he has obtained his BSc from Calcutta University in 2007 and MSc from IIT Kanpur in 2009. And subsequently, he moved to get PhD in 2012 from Ludwig Maximilian University at Munich, Germany, under the guidance of Professor Herbert Mayer. And subsequently, after obtaining PhD, he has moved to postdoctoral fellows from 2013 to 2015 at Chuba University with the Professor Yamamoto. And again, in 2016, he has obtained the Alexander Van Humboldt Fellowship and worked with Professor Frank Glorious at Münster University, Germany. And 2016 to 21, he is assistant professor at IISER Kolkata. And since 2021, he is associate professor at the same institute. And he has many awards and honors. And 2021 itself, he has received so many awards. Young Investigation Award sponsored by the Molecules, and Merck Young Scientist Award runner-up in Chemical Sciences, and INSA Medal for Young Scientist, and Associate of the Indian Academy of Sciences, and all these in 2021. And 2020, he is a recipient of NACI Young Scientist Platinum Jubilee Award in Chemical Sciences, and 2019 Theme Chemistry Journal Award. And Professor Maji's research interest is organic synthesis, catalysis, and mechanistic studies. And today's his talk is constructing 3D molecular architectures through visible light energy transfer catalysis. With this brief introduction, I welcome Professor Maji to deliver his talk. Professor Maji.
Well, thank you very much for this very nice and generous and very kind introduction. So I hope the screen is visible, right? So I'll make it full screen. It is visible, right, in full screen mode?
Yeah.
Okay, so then first of all, I'd like to thank Shukalnanda for inviting me into this platform, and also all the organizer of CMCRI and JSPS Society. So this is an excellent platform I am having, and then from these mornings I'm listening to the excellent talks, starting with CH bond activation, asymmetric catalysis, and then the last two talks on asymmetric organocatalysis. So this is very, very fantastic and highly knowledge gaining. Now in this presentation, so I will be talking about visible light energy transfer catalysis, so particularly the photoredox and the energy transfer catalysis. So before I move ahead, so this is the activity of my group. We have a small and very young group, and major part of my group actually work on this fast flow tungsten metal based catalyst development, particularly with the manganese. And another half of the group actually they work on photoredox tungsten metal dual catalysis, so that includes the photoredox and also the energy transfer reactions. We work a little bit on asymmetric synthesis and also using the chiral metal complexes. And of course, so as a trained physical organic chemist, so I try to investigate the reaction mechanism as a whole. Now in this presentation, so I'll be talking about the visible light catalysis, and then I don't need to give an introduction that why people will be considering the visible light as a source of renewable energy. Now all the motivation and the learning actually comes from these billions of years old enzyme and then the photosynthesis that give us the food for the whole planet. And for renewable energy sectors, so people has learned to harvest the energy to generate the electricity in a green and milder way. Now as a chemist, so we also try to mimic the biological system. Now for a organic chemistry per se, so as you know that most of the organic molecules, so they are not capable of absorbing the visible light. So in that case, so we need to use a catalyst, or in this case, one can say that those are the energy harvester or the sensitizers that will do the job of absorbing the visible light and do the chemistry out of it. Now from a chemistry perspective, so those molecules can be tungsten metal complexes, organic dye, or the semiconductors. Now, if I go through a general mechanism for this, so I have chosen here one iridium-based photosensitizer, so that absorb a visible light close to 400 nanometer light. Now, this sensitizer, so upon excitation, so that actually promotes an electron from metal center orbitals to the ligand center orbitals in its excited state. Now, this excited state is long-lived, and now, due to this excitation, so because this promotes an electron in higher energy orbitals, so there is a higher energy orbital electrons in the high energy, and there is also a vacancy. So that means this excited state of this molecule can simultaneously act as an oxidant, very strong oxidant, and as well as strong reductor. Now, if we put some donor, for example, in this case, I put an example of an amine. Now, this amine can inject one of the electron to these lower energy orbitals, and that left with an electron in the high energy pi star orbitals. So that eventually all this process actually lead to iridium in its formal 2 oxidation state. Now, if this formal 2 oxidation state is generated, one is come back to the ground state. These high energy electrons that actually generate a very, very strong reduction potential. So that is, for example, for this particular example, this is close to minus 1.4 volt. Now we have the whole control of choosing this sensitizer and the light sources, whatever the available, and we can tune this potential coming out of it in a spatiotemporal manner. Now there are a lot of development based on this using these photoredox chemistry for doing the various transformation. And in this case, I will talk about one example from my lab. So what we did, so we used this reducing equivalent to reduce the cobalt to its lower oxidation state and use this for a carbon-carbon bond forming event. To be specific, so I choose this example. So I love this example because this also fit into this community. So today, Santunada talked about the desymmetrization reaction. So we have this molecule. So this has a 2 chiral center, but there is a double bond. Now, if we can do this coupling between these 2 alkene, so we can generate 3 chiral center, and eventually we actually desymmetrize this molecule. Now, this is a 2+2 reaction, but that is mediated by cobalt-1, and as I said, this cobalt-1 can be generated by employing this photoredox cycle. Now this cobalt-1, so that can coordinate between this alkene, one of the alkene partner, and another alkene partner, and then this chiral ligand we can choose, and that tunes the property, and that also gives the enhanced selectivity. These 2 oxygen center that occupies the axial coordination, that gives the diaster selectivity, and we can obtain very high enhanced selectivity and diaster selectivity for this reaction. Now, not only this, so we used this cobalt catalysis for different reactions also, like anion coupling. This is intermolecular, and the intramolecular, in this case also we can control the stereochemistry at this center. Not only cobalt, we can do this same chemistry with the nickel. So the idea is the same. So we have a very reducing equivalent that is generated in a controlled manner by using a photoredox and a mild organic sacrificial electron donor. And there also we can generate the nickel in its low valent oxidation state, and we can do the cyclopropanation reaction or the multi-component functionalization of this unactivated alkene. Now, what happens if we don't have an electron donor or the acceptor? So this molecule goes to its excited state. Now there is no donor or acceptor. So in this case, what happened? It can come back to its ground state and emitting a light. Now this light emission that can be very, very useful for organic material and the light emitting devices, but for organic chemistry per se, so that is a waste. Now another phenomena can happen that it comes back to its ground state, and if there is a substrate with a suitable triplet energy to that of this excited molecule, then the substrate can go to excited state, and particularly the triplet state, and then for the organic chemistry, so that the energy transfer follows a Dexter mechanism, so then it will be very, very useful. Now, I would like to use this triplet energy transfer chemistry and for this like context of this talk for creating 3D topology. Now for that, so nothing better than the cycloaddition reaction, and here I have depicted the classical 2+2, 2+3 and 4+2 cycloaddition reaction, and that gives us beautiful 3-dimensional rings, so be it the 4-member ring, 5-member ring, or the 6-member carbocyclic or the heterocyclic rings. Now, one common feature of all these reactions are they are very, very atom economical. So 2+2 gives a 4 atom, no addition or no deletion, nothing lost. Now, another common feature for all these 3 reactions I have shown here. So here we are breaking a pi bond and we are forming 2 new sigma bond. Now, that energy that is derived from the formation of this sigma bond, that is actually compensating the energy that is lost for the breaking of the pi bond. And all these cases, so these reactions are thermodynamically driven. Now, if I come back to that same reaction for another molecule, so for this case, I have depicted this molecule is a naphthalene. So this is a class of heteroaromatic, class of polyaromatic hydrocarbons. So they are abundant, they are feedstock chemicals. Now, if you see the topology, so these molecules also have this pi electron, for example, this diene fragment. Now, if one consider this 4+2 cycloaddition reaction to this molecule, now this is a 3D rich molecule compared to this flat 2D aromatic molecule. Now, here it comes the problem, because now this red sigma bond, that energy released by making this red sigma bond is not compensated by the loss of this aromaticity. So in this way, this reaction is actually energetically uphill. Now this is the scenario over here. So we have a reaction where the product is higher thermodynamic energy than the starting material. So that accounted that if the kinetic barrier that is required for the forward reaction, that is actually always higher than that is required for the lower reaction. So that means these reactions are always tend to be in equilibrium, favoring the starting material. So whatever we do to lower the kinetic energy for the forward reaction, that will be enough to bring the molecule back to the starting material. So it's very, very difficult to trap this product kinetically. So in that case, the product yields are always lower. Now one can think of doing this reaction by applying the light. So in that case, we can excite the molecule by applying a suitable wavelength of the light that depends upon the chromophore exists here. So for example, in this naphthalene case, so the chromophore is like close to 300 nanometers. So we need to supply the 300 nanometer light that goes to the excited state. Now, if we do the reaction in the excited state, have this blue light. So at least from this excited to the product, so this is energetically favorable. But the problem, there are multiple problems. One of the problem is that this 4+2 cycle addition reaction, whatever I shown here. So now this is symmetrically formatted. So at least the concerted reaction, the stepwise reaction can be allowed. But there are two other possibilities. So instead of having this 4+2, one can have this 2+2 cycle addition, and one more. So where we can have this 3+2 cycle addition or the meta cycle addition, where this adenophile react at this carbon center 2 and this carbon center 4, and that gives very intricate array of three-dimensionality. Now the product structure from this excited state, so this 4+2 is actually not allowed, and these two cases it is allowed, but the product, whether it is 2+2 or the 4+2, that depends on multiple parameters. And mostly if the adenophile or the arenes are non-polarized, so these meta adducts are favored. If it is a polarized, the ortho adducts are favored, but that depends upon this Euler equation. So we need to think about the ionization potential, redox potential, and the orbital interaction. Now another way of doing this reaction, so instead of directly using directly exciting the molecule by using the high energy light, like for example, I talked about 300 nanometer UV light. So one can apply the visible light and use this energy transfer catalysis cycle that I showed before. So in this case, so we can use a sensitizer that will be excited, goes to its Tipler state. Now from this Tipler state, it can excite the starting material to its Tipler state. Now we can have this reaction from the Tipler state. Now in this case, so even this 2+2 or the 4+2 can be symmetrically allowed in a stepwise manner. Now in this presentation, so I will talk about this case and taking a case study. And one case study we did in our group for using this acetyl naphthalene group. So as I said, that this photosensitizer goes to its excited state. Now as it comes back to its ground state, this excites this acetyl naphthalene to its Tipler state, and this Tipler state is stable and is stabilized because of this acetyl group. And what we did, so we are able to catch this Tipler state by using a styrene in a stepwise, one bond at a time. So we form this carbon-carbon bond, then intersystem crossing, and the second bond forming event to give this 4+2 cycloadducts, very interesting three-dimensional molecule. Now, if you look into this transformation as per se, so we start with this acetyl naphthalene. So it's a 2D feedstock. Now, by doing this reaction, so we did increase the three-dimensionality in this molecule, and this reaction is actually endothermic. So we are able to catch this endothermic molecule because this has a higher triplet energy than that. So this catalyst can excite this starting material only, not the product. So now this product is actually formed as a kinetics trap species, and we could column it out and purify, do the characterization, and even we can crystallize. Now, I would like to stress upon the challenges that we solve in this reaction. So as I said, that we are getting this 4+2 or the paracycloadduct, and in this case we are not getting the other two, so the meta or the ortho. Now there is another challenge because of these two substituents here. So these two groups can either be in this position, so I call it as a distal, and or it can be in this way. So it is a proximal. Now we are getting the distal adduct selectively. So we have an excellent regiochemistry in this reaction. But the diaster selectivity, so where this aryl group or this substituent, whether it is towards this arene ring or the outer side, so you call this as the endo or the exo. Now in this case, because this is a typical 1-1 forming at a time, so that diaster selectivity is actually poor. So we observe 2:1 diaster selectivity. Now little bit more about the reaction development. So we studied the UV absorption spectrum. So now, as you can see, so there is no agglomerization happening in this case, and there is a very tiny absorption at the 370 nanometer. So if we excite the molecule at 370 nanometer light, so we get this product, but the yield is lower. But our target is to do at a visible light. So if we excite this molecule at a visible light, so none of the products are detected. Now, if we use the sensitizer, so in visible light, so using this sensitizer, which has a higher triplet energy than that of this acetylnaphthalene, so we could able to get these products exclusively and a 2:1 diastomeric ratio. Now, we confirm that this is a triplet energy transfer event. So we studied the cyclic voltammetry, and then from this cyclic voltammetry, it is confirmed that the electron transfer from the photocatalyst to the substrate or the electron transfer from the substrate to the photocatalyst, these are outside the thermodynamic window, so it does not happen. And we also did this triplet quencher study. So if we put a oxygen or 2,5-dimethylhexadiene as a triplet quencher, the reaction completely shut down. That gives indirect evidence that this reaction is actually going by a triplet energy transfer mechanism. Now we studied the kinetics. So the product formation and the decay of the starting material, they follow almost the same rate. That indicates that at least in the NMR time scale, there is no intermediate is being formed. The scope of the reaction is very broad. So it works for all the styrene, so be it electron donating, withdrawing, or heteroaromatic substituent. It also works for the variety of acetyl-naphthalenes, including this heteroaryl substituent. It also works for these esters and also for the amides, and that I'm not showing it here. But this acetyl group is necessary. Without the acetyl groups, the reaction did not work at this moment. Now we can put some of the bioactive molecules so to demonstrate that the scope of the reaction. So that bioactive molecule that includes the fibosyl, chlorofibrillic acid, phenbufen, ketoprofen, oleic acid, menthol, borneol, and cholesterol. So all these substituent, when it is attached to the molecule, they do not interfere with the reaction outcome. Now we also play more with this. So we have this molecule, so now we can functionalize it, so we can reduce it to increase the three-dimensionality even more. We can do the Michael reaction, we can do the cyclopropanation reaction or the epoxidation reaction. In all cases, the yields and the selectivities are relatively very high. Now, recently we actually surveyed this field. So, and we have summarized the availability. So this field is very, very growing in last 5 years or so. And there are large numbers of reactions are already being reported. So not only the polyhydrocarbons and also heteroaromatic compounds. And the reactions are mostly like 4+2 or a 2+2 variant. So that I summarize here. So most of the reaction reported in last 5 years or so, this is either 2+2 cycloaddition reaction or the para 4+2 cycloaddition reaction. Now, as I said, this 3+2 cycloaddition, that gives a very, very intricate array of three-dimensionality starting from these aromatic compounds. So that is not being reported as far. Now, we take up this challenge. Now, before I go to this, so I would like to talk about this 3+2 cycloaddition reaction. Now, as I said that this is a photochemically allowed by orbital symmetry. So classically, this reaction goes as follows. So you have a aromatic compound. So that goes excited to singlet excited state. So direct excitation by using a UV light. Now, this excited state is forms a excitase with the arenophile. Now this excitase, it collapses to keep either a polarized transition state or a biradical, that depends upon the substituent present, and from this biradical, so that gives the carbon-carbon bond forming event, and that gives the 3+2 cycloadduct. So it's a stepwise process, but that the key information over here that this goes in a singlet excited state. Now, what we thought that we can selectively get this paracycloadduct. Now, to go to this paracycloadduct to this metacycloadduct, so this is a one excitation. So we have a triplet energy transfer catalysis that I showed. So that gives the paracycloadduct, which is energetically upfield. Now, if we can excite this paracycloadduct by somehow clean this red bond and connect it over here, so in that way we should be able to get this metacycloadduct. Okay, so what I said that we have this paracycloaddition reaction that the mechanism I have discussed just now. So this is a like excitation carbon-carbon bond forming event that gives this 4+2 cycloadduct. Now, if we excite this 4+2 cycloadduct, unlike the previous study, so while we did not excite, we choose a photosensitizer in a way that we did not excite it. Now, if we excite it, so we'll be able to form this biradical. Now, this biradical can rearrange itself to give this allyl radical and benzyl radical. Now, we break this red bond. Now, if this atom connectivity, this benzylic radical connect with this carbon number 2, so then we could get this intermediate, and then from there, so if a carbon-carbon bond forming event happens, so that should give us this 3+2 cycloadduct formally, and we'll have to do this whole process in a cascade manner. Now, this is the drawing in a paper and pen. Now we computed these possibilities. Okay. Now this diagram is very, very complex. Okay. Now if I slowly go through it, so this is the excitation of this starting molecule. Now this is the 4+2 cycloaddition reaction that I talked about. Now this is the triplet state. It goes the spin crossover in a singlet surface that gives this 4+2 cycloadduct. Now what we are thinking, so we wanted to excite it again to go to this triplet state. Now from this triplet state, we want this bond to be cleaved. Now this bond cleavage can happen in a two mechanism. So either a direct cleavage goes to this intermediate that I told earlier. This is triplet B intermediate. Now from there, this bond forming event that gives to this product. Now the computed state says that these are energetically actually viable. The alternate possibility is that these undergo a dipi-methane type rearrangement. So classical dipi-methane type rearrangement, and that goes in the triplet surface, and then again it goes to the same product formation. Now either possibilities are okay, so both possibility leads to the same product formation. Now the 2+2 product formation did not happen, so that we have computed, and that requires higher energy. So now the key feature for these two is these two intermediates. One is this singlet intermediate, this B, another one is the triplet B. Now in the singlet B, we are getting this 4+2 cycloadduct, and from this triplet, we are actually getting this 3+2 cycloadduct. Now we check the spin density for this. Now this is the singlet state, this intermediate. Now if we check the spin density, so this benzylic position and this position, so that actually they have the highest spin density, and that actually leads to the bond formation, and that gives the 4+2 cycloadduct that we observe in the experimental condition. Now in the triplet state, the orbital coefficient change. Now the spin density, so this is the positive phase, and the actually in the this carbon number 2, that which I denoted as a C meta, that has the negative coefficient that leads to the bond formation, and that actually gives us this 3+2 atom. Now this is a very, very long story short. So this is the optimization. Now this is the starting material we have chose. Now we excite with a different photocatalyst, and that can give either this 4+2 adduct or the 3+2 adduct. Now we have computed the triplet energy, so of the starting materials and the product, both the products. Now what we found that if we take a photosensitizer like this 4CZ IPN, so it has a very low triplet energy 53, which can excite this molecule, not that molecule. So in that case, we are getting this 4+2 adduct selectively, and we are not getting this 3+2 cycloadduct. Now, as we increase the triplet energy and as we reach this thioxanthan molecules, which has a higher triplet energy than this adduct, so now this thioxanthan sensitizer that can excite both the starting material and the product, and that actually lead to this isolation of this 3+2 cycloadduct. But thioxanthan triplet energy is lower than that of the product, so we are able to trap this 3+2 cycloadduct selectively. Now, if we choose another sensitizer, this molecule, xanthone molecule, which has a very high triplet energy, now that actually lead to this product, but again, decomposition of the product, and in that case, we get a lower yield. Now, again, in this case, so we have confirmed the structure. So this is very, very interesting molecule. So we have a ring system here. The 5-5 ring systems are fused that is connected via this 3-member ring, and this is this another oxygen ring over here. And these two arene rings are actually pointing to each other. So this is the major diastereoisomer, and in the minor diastereoisomer, these arene rings actually pointing away. Now, in this case, so we did the control experiment again to prove that this is actually happening via a triplet energy transfer mechanism. So similarly, we did the CD experiment. And the CD experiment suggested that energy transfer, electron transfer from the photocatalyst to the substrate or from the substrate to the photocatalyst are not happening. So we need the light photosensitizer. Without that, there is no product. Even if we heat it, there is also no product. This geometry of this alkene fragment has a little influence. So we can take either the E alkene or the Z alkene. The yields are relatively similar. Now, if we run the reaction in presence of triplet quencher, so again the reactions are down. That also gives us a hint that this reaction is actually going via triplet energy transfer mechanism. Now, we again studied the kinetics of the reaction. Now, what we observe that the this consumption of the starting material is very fast in the kinetic in the NMR time scale in an NMR experiment. Now, we observe this 4+2 cycloadduct. So that is growing initially, it is reach a maxima and then slowly goes down, and the 3+2 cycloadduct is actually slowly going as this 4+2 cycloadduct is going on. Consumed. So this is a typical example of a consecutive reaction. So the starting material first comes to this intermediate 2. This is the 4+2 cycloadduct, and that actually consumed to gives this 3+2 cycloadduct. Now, what we also did, we have isolated this 4+2 cycloadduct, and we have subjected to the reaction condition, and that gives very high yield of this product. Now, this reaction does not happen without the photosensitizer. Now, this is not a thermal reaction. So if we take this molecule and if we heat it at 60 degrees centigrade, there is nothing happens. So if we heat it more, this also decomposes, but it does not give to this 3+2 cycloadduct. Now, the reverse reaction. So if you take this 3+2 cycloadduct, now if you shine light in presence of sensitizer or in absence of sensitizer, there is nothing happens. Now, if you put 1000 stronger photosensitizer, that leads to the decomposition of the product, but it does not reverse back. So this is actually a kinetically trapped species. So this is a 2-photon excitation scheme, but it happens in a stepwise manner. So first goes to the excited state, gives this paracycloadduct or the 4+2 cycloadduct, and again this goes to the 3+2 cycloadduct upon exciting or upon getting one more photon. Now, to prove that, we actually studied this reaction. So we performed the kinetics initial rate. Now, what we did, this blue line, so we put a 1 5-watt LED light and measured the rate. And then what we did, we put 2 5-watt LED light and we measured the rate. Now, as we increase the power, so that we have found that the rate is actually quadratically dependent on the power of the light. So that indicates that we have 2 photons actually used in the reaction, and the photon is actually a reagent for this process. Now, that comes the scope of the reaction. The scope is very, very broad. So it works for all the substrate that you have studied, and it also works for some of the interesting molecules. This molecule we can derivatize, so like the Baeyer-Villiger oxidation reduction, we can cleave this bond by putting HBr in acetone, and also we can cleave this middle bond, and that gives a very interesting 3+3+3 ring system. Now, we also work on the heterogeneous catalysis. So this is outside of this conference. So in this case, we have shown that if we place this redox active metal in close proximity, that actually increase the rate and the efficiency. So we said that proximal driven catalysis, and then that we have applied for the CN coupling reaction. And in another case, so we have shown that if we put a photosensitizing unit itself in the heterogeneous platform, so that actually can act as the energy harvester itself. So we said this as an interlock catalyst, and this interlock catalyst can enable diverse range of cross coupling reaction. So one particular example I would like to show it over here. This is the CO coupling reaction. Now the accepted mechanism goes as follows. So we have an oxidative addition, ligand exchange. Now from this nickel to reductive elimination, particularly this CO reductive elimination, that is very, very high energetic process. Ruping did the computation for this, and that actually requires close to 30 kilocalorie per mole energy. So for that, one actually need to heat it very high, so close to 140, 150 degrees centigrade, and also require very, very bulky ligand. Now there is a work going on. So instead of heating this nickel to intermediate, so we can supply the energy. So that is the triplet energy transfer mechanism that I showed. And in this case, we have already found that this POF is very good actually transferring the energy, and that gives this excited nickel species, and that actually facilitates the reductive elimination. And we have found that this catalysis is very good. So this is this material with a 1% nickel loading, that is very, very high yield of this CO cross coupling reaction. And this is actually comparable with the homogeneous system, which requires a very high loading of the nickel. The scope is very, very broad, so that I will not discuss because of the lack of time. Now in this presentation, so I was able to convince you that this photoredox or the light can be used as an energy source to drive chemical reactions. So be it photoredox, where the electron transfer event is being taking place, or the energy transfer catalysis, so where the energy that is available in the visible light can be mediated by photosensitizer to the substrate, and that can be used for the generating three-dimensionality. Now with this, so I would like to acknowledge my group actually who actually did all the hard work, and I am here presenting here before you on behalf of them. So I am very, very grateful for their hard work, and I'm also thankful to all these funding agencies who actually generously supported our research, and also our collaborators. So Gorima's example I have shown, and finally, I would like to thank you for listening to me. So I'll be happy to answer your question. So if you have any, or if the time permits. Thank you very much.
Professor Maji, and maybe I will ask the audience if anybody want to have any questions. Only one question can raise their hands. Okay, if there is no question from audience, Maji, I have one question. So this light promoted reactions, have you scaled up to some gram scales, or it requires the same light, or you need more number of lights?
Yeah, thank you very much for this question. Actually, it's a very interesting question. Now, the light promoter reaction has a limitation. One limitation is that the reaction depends upon the surface of the reaction vessels. Okay, so as we scale up, so the reaction vessel surface is increased. So we need to put more number of lights to cover the surface. We can do the gram scale, but in that case, we need to put more lights. Okay. Now, another way of doing it, so we did for 1 or 2 examples now at this group, so that is not published yet. So we can flow the reaction. So in that case, we can use one light source, but by controlling the flow, so we can control the time that is required for the light to be absorbed. So in that way, we can also do.
Okay, thank you. So if no more questions, and then we can move on to the next speaker.
Thank you very much. So,
yeah, thank you. Professor Sai, are you?
Yes.
Yeah. So welcome to this webinar. And Professor Mahashira Sai studied organic chemistry at Tokyo University under Professor K. Oshima and Professor M. Matsuhara. After receiving his PhD in 2012, he joined Professor Yamamoto's group at Chibu University as a postdoctoral fellow. and worked on organocatalysis, especially on chiral brown-state acids. He then moved to Research Foundation ITSU laboratory, where he worked as a research associate for 3 years. In 2019, he was appointed as a tenure-track assistant professor at Gifu University, where he started to develop new organic reactions using earth-abundant alkali metals such as sodium and potassium. In 2023, he became an associate professor at Shimane University, Japan, and in 2024, he received the Theme Chemistry Journal Award. His research focuses on development of new organic reactions using metals that are earth-abundant, inexpensive, non-toxic, and highly reactive metals. With this brief introduction, I welcome Professor Sai to deliver his talk on recent advances in potassium-mediated organic reactions. Professor Sai.
Hello, everyone. Can you hear me?
Yeah. Go ahead. Yes.
Thank you for generous introduction. I'm grateful for the opportunity to present at this wonderful webinar today. I'd like to extend my thanks to all those involved and to Professor Skalyan for inviting me. Now, as indicated here, the research topic I will be presenting today is on new organic reactions involving potassium. Transition metals represented by palladium and nickel have played a central role in organic chemistry for a long time. However, transition metals have several drawbacks, including limited resources, significant environmental impact, high cost, and strong toxicity. On the other hand, alkali metals have attractive features such as abundant resources, low cost, low toxicity, and high reactivity, but their use in organic synthesis has been limited to simple Brensted bases. Therefore, we began research to discover unique reactions specific to alkali metal, especially potassium. Today, I will present two reactions, one involving chiral potassium-based catalyst and the other involving potassium homoenolate equivalents. Chiral transition metal catalysts have been widely employed in asymmetric reactions. Generally, these catalysts offer high reactivity and can readily modulate reactivity and selectivity through combination with various chiral ligands. However, transition metals have drawbacks mentioned. On the other hand, since the 2000s, various organ catalysts have been developed. These catalysts do not contain metals, offering the advantage of avoiding the limitations associated with transition metals. However, they often suffer from low reactivity, leading to limitations in substrate scope. Therefore, by synthesizing chiral alkali metal catalysts with high reactivity and without the drawbacks associated with the transition metals, we aim to achieve asymmetric reactions that were difficult to accomplish with both chiral transition metal catalysts and organ catalysts. Alkali metals have low electronegativity, which enables them to form ionic bonds with other atoms. Consequently, the anion paired with alkali metals exhibit high reactivity. Therefore, we aim to synthesize a chiral potassium-based catalyst by combining high reactive potassium-based with a chiral ligand. The choice of chiral ligand would be crucial, and we focus on crown ethers. They are well known to coordinate to lithium, sodium, and potassium cations depending on their cavity size. Thus, we hypothesized that by synthesizing appropriate chiral crown ether, we could successfully create a chiral environment around the potassium cation. In Yamamoto lab, I was engaged in the synthesis of binol-based chiral Brensted acid like this, and in developing new reactions using these acids. So I tried to synthesize binol-based chiral crown ethers by utilizing these experiments. We show synthetic route to chiral crown ethers here. First, the hydroxy group of binol are protected by mom groups, and the 3,3' position are then related. Subsequently, Suzuki coupling with appropriate L bromides followed by the protection of the mom groups provide these binols. Finally, coupling with such diethosylates gives the desired chiral crown ethers. These chiral crown ethers are stable and low hygroscopic solids that can be purified by column chromatography.
To evaluate the catalytic activity of chiral potassium-based catalysts, we focus on the asymmetric intramolecular oxidation microreaction of epsilon hydroxy alpha-beta unsaturated carbonic compounds as a model reaction. In 2011, Asano and Matsubara achieved the conversion of epsilon hydroxy alpha-beta unsaturated carbonic compounds into chiral tetrahydrofurans using a thiourea catalyst derived from cinchona alkaloid. However, only highly active ketones are used in their study. In 2013, Takemoto et al. Accomplished the asymmetric cyclization of less reactive esters using an N-sulfonyl guanisine catalyst, but the product yield was only 45% yield, and reaction time required 7 days. Therefore, to demonstrate the utility of our chiral potassium-based catalyst, we aim to show that using these catalysts can achieve the asymmetric cyclization of esters with high yield, high selectivity, and shorter reaction times. We conducted an asymmetric cyclization reaction of substrate 1 to product 2 in the presence of potassium tertiary peroxide and various chiral crown ethers, evaluating the activity of these chiral crown ethers. Generally, introducing bulky substituent of the aryl rings at the 3,3' positions of vinyl had a beneficial effect on enantiomer selectivity. Finally, we found that using chiral crown ether L7, which has 3,5 ditertiary butyl substituted aryl groups as R, exhibited the highest enantiomer selectivity of 90 to 10. We investigate the substrate scope and the optimal conditions. Various epsilon hydroxy alpha-beta unsaturated esters were smoothly converted into chiral tetrahydrofurans with good yield and enantiomer selectivity, regardless of the electronic properties of the aryl moiety. Unfortunately, the reaction of alphatic ester was sluggish, with almost racemic product 13 obtained in only 14% yield. To further demonstrate the synthetic utility of this system, we explore the asymmetric cyclization of Z-hydroxy alpha-beta unsaturated esters to chiral tetrahydropyrans. To the best of our knowledge, there have no reports on the asymmetric cyclization of alpha-beta unsaturated esters containing alpha-dic OH at the zeta position. The cyclization of Z-hydroxy alpha-beta unsaturated ester 1 did not proceed at -78 degrees, but at -40 degrees, the derived tetrahydropyran 2 was obtained in 87% yield with 82 to 18 ER. Various Z-hydroxy alpha-beta unsaturated esters were smoothly transformed into chiral tetrahydropyrans with good yield and enantiomer selectivity at -40 degrees within 2 hours. To understand the reaction mechanism, several control experiments were performed. First, product 1 was reacted with 10% potassium tertiary peroxide at -78 degrees for 2 hours to investigate whether racemization of 1 occurs via base catalyzed retro microaddition sequence. The results showed that racemization of 1 was not observed under these reaction conditions, and the ER was contained. In the previous reaction, we used substrate with E configuration. So we decided to investigate how substrate with Z configuration would affect the reaction outcome. Asymmetric cyclization of Z1 and optimal conditions resulted in only 10% yield of 2 with an enantiomeric ratio of 58 to 42. This result suggests that coordination of the substrate carbonic oxygen to the potassium cation is essential for high yield and asymmetric induction. In contrast to transition state 2 derived from E1, transition state 1 derived from Z1 faces difficulties in adapting such conformations. To further examine the influence of crown ethers on the conversion, we carried out the cyclization of 1 in the absence of crown ethers, resulting in a drastic decrease in the yield of 2 to 40%. In this case, a 10% yield of 1 naphthol was also detected, which was equivalent to the amount of potassium tertiary butoxide added. The addition of 18 crown 6 and L7 improved the yield of 2 to 70% and 85% respectively, and suppressed the formation of 1 naphthol. These results suggest that the catalytic deactivation pathway involves transesterification of potassium alkoxide A with 1 and O2, leading to the formation of potassium 1 naphthoxide. Once the less basic potassium 1 naphthoxide is formed, it cannot participate in the catalysis cycle again. So sterically bulky crown ethers are considered to prevent this undesirable process. We collaborated with Professor Udagawa at Gifu University to perform calculation to investigate how chirality of this reaction is induced. This figure illustrates the distances between the potassium cation and 6 oxygen atoms contained in the chiral crown ether, along with the energy of the complex. The 6 oxygen atoms are distinguished by 6 different colors. As seen on the right side of the figure, when the distance between the potassium cation and one of the 6 oxygen atoms increases, the energy of the complex also increased. Conversely, when the energy of the complex is low, it indicates that all 6 oxygen atoms are close to the potassium cation. Therefore, it seems energically unlikely for a chiral crown ether, once coordinated to the potassium cation, to dissociate and form free potassium cation. The calculations are still in progress, but we show the transition state. The result indicates that in this reaction, the tethered moiety of the substrate is positioned in an open space to avoid steric repulsion with the bulky substituent of the crown ether. Circulation proceeds from this transition state, leading to the formation of the R product. The products are versatile intermediate because the ester group can be readily converted into diverse functional groups without loss of the enantiomeric purity. For instance, ester 1 could be transformed into the alphatic ester 2 by treatment with benzyl alcohol and DBU. Palladium catalyzed CO bond cleaving coupling of 1 with phenylboronic acid was also possible, which afforded to ketone 3. Amide 4 was also obtained by the reaction of 1 with 2,4-dinitroaniline. Beta reduction of 1 followed by protection of the gelatin alcohol led to the formation of benzyl ester 5. Next, I will present the second research topic, which is about potassium homoenolates. Metal enolates are variable nucleophiles because they can selectively introduce electrophiles at the other position of carbonic compounds. On the other hand, metal homoenolates are equally useful as they can also introduce electrophiles at the beta position of carbonic compounds. However, the utilization of homoenolates in organic synthesis is significantly limited compared to enolates. This limitation arises from the fact that while enolates can be easily prepared by reacting carbonic compounds with a base, no such precursors exist for homoenolates. The most widely used method for preparing homoenolates currently relies on the cleavage of cyclopropane rings. In the 1970s to 1980s, Nakamura and Kawajima demonstrated that cyclopropanone acetate and silyl-protected cyclopropanol are effective precursors for the generation of homoenolates. Furthermore, since the 2000s, Cha has succeeded in developing reactions using unprotected cyclopropanols as homoenolate precursors. Inspired by these pioneering studies, the chemistry of metal homoenolate using cyclopropanols as precursors has made significant progress in recent years. However, there are some issues with the preparation of homoenolates using ring opening of cyclopropane. These include problems with the synthesis of starting materials and the selectivity of ring opening of unsymmetrical cyclopropanes. In particular, homoenolates prepared by this method have low nucleophilicity and only react with highly reactive electrophiles. To improve nucleophilicity, ring opening reaction using lithium or sodium bases has been studied, but they could not be used for beta functionalization because the equilibrium favors cyclopropoxides over the homoenolates. We believe that this problem could be solved by utilizing dianions of ketones, specifically by electronically protecting the carbon moiety. Intermolecular cyclization reaction can be prevented. These dianions act as highly nucleophilic ketone homoenolate equivalents, so allowing for the synthesis of beta functionalized ketones. With this concept in mind, we focused on preparing highly reactive ketone dianions from readily available precursors, particularly allylic alcohol. In the course of previous studies using potassium bases, it had been observed that potassium carbanions could deprotonate CH bonds that are inert to conventional strong bases. Therefore, we anticipated that by treating allylic alcohol with potassium carbanions, the proton on the hydroxy group and the proton at the C1 position would be abstracted, resulting in the formation of the desired potassium dianions. This potassium dianion, being a highly reactive potassium homoenolate equivalent, is expected to react with various electrophiles at the beta position to yield beta functionalized ketones. To achieve the desired reaction, it is necessary to find the base that can efficiently convert the allylic alcohol into dianions. Therefore, we initiated deuterium labeling experiment to identify suitable bases for such transformations. If dianions are indeed generated from allylic alcohol 1, the introduction of deuterium at beta position should occur upon reaction with deuterated water. Furthermore, we anticipate that the remaining enolate moiety would react further with deuterated water to give ketone 2 with deuterium incorporation at both the alpha and beta positions. When this deuterium labeling reaction was conducted using 2 equivalents of Schlosser base prepared from normal butyl lithium and potassium tertiary peroxide, we successfully obtained the desired ketone 2. And to our delight, it was found that deuterium had been introduced almost completely at both the alpha and beta positions. However, the yield was moderate, with a significant amount of starting material. So we increased the amount of the Schlosser base to 4 equivalents. But this did not significantly improve the yield of 2. The reason of this was not clear, but since the Schlosser base is generated in situ mixing normal butyl lithium and potassium tertiary peroxide, it's difficult to precisely adjust the ratio of each component. Alternatively, it was considered that the Schlosser base might have a more complex structure than anticipated. So we tried to synthesize isolable potassium carbanions. As a result, when we prepared trimethyl methyl potassium and used it in the reaction, the desired ketone was obtained in 86% yield with complete consumption of the starting material. In contrast, reaction using lithium carbanions such as normal butyl lithium or tertiary butyl lithium, which are conventional strong bases, did not proceed at all. Furthermore, no reaction occurred with potassium amides or sodium carbanions, indicated that potassium carbanions are essential for this reaction. Next, we investigated the scope of electrophiles. The potassium dianions derived from allylic alcohol 1 could capture various electrophiles. The dianion react with carbon and related compounds included aldehydes, ketones, imines, formamides, vinyl amides, nitros, affording the corresponding products in moderate to good yield. Additionally, alkyl halides active alkenes and epoxide could also be used as electrophile. Furthermore, it also reacted with gaseous carbon dioxide to give gamma-ket acid. In this reaction, not only carbon electrophiles, but also heteroatom-based electrophiles were applicable. This enabled the fossil synthesis of ketones bearing boron, silicon, tin, phosphorus atom at the beta position. The extremely high nucleophilicity of the potassium dianions offers a significant advantage in its ability to react with less reactive electrophiles. But it also presents a challenge when electrophiles are highly reactive, often resulting in complex mixtures. To address this issue, we consider that the addition of other metal salt to the potassium dianions would lead to the formation of dianions with milder nucleophilicity that could tolerate such electrophiles. Indeed, when lithium bromide was added to potassium dianion A, followed by reaction with diphenyl disulfide, the desired ketone 2 bearing a phenylsulfonic group at the beta position was obtained. Notably, without lithium bromide, this reaction yielded complex mixture. Additionally, upon adding zinc chloride to the potassium dianion A, followed by reaction with benzoyl chloride, the reaction proceeds at the internal carbon and it results in the formation of branched product 3. Next, we investigate the scopoaric alcohol using one of these highly reactive electrophiles. Regardless of the electronic properties of the aryl group, polyhydric alcohol provides the desired product in good yield. Additionally, arylic alcohol containing heteroaryl groups were also applicable. We further examined the substituent at the C3 of the arylic alcohol and found that substituent at this position did not significantly affect the reaction outcome. In the method utilizing ring opening of cyclopropanols, less substituted carbon ions are typically formed via an ionic mechanism, making the synthesis of products like 11 challenging. However, our method allows for the faster synthesis of such compounds. When arylic alcohol with alkyl groups as the C1 were used, the reaction did not proceed and the starting material was fully recovered. This is likely because the potassium dianion cannot be stabilized by conjugation when aryl groups are not present. Since our potassium dianion has 2 nucleophilic sites, the enolate moiety remains after reacting with the first electrophile at the beta position. Therefore, we hypothesize that sequential addition of different electrophiles could achieve one-pot functionalization at both alpha and beta and alpha position. Furthermore, by using silicon electrophiles with high oxygen affinity as a second electrophile, we also envision the synthesis of C3 functionalized silyl ethers. We first attempted the synthesis of alpha-beta difunctionalized ketones. After reacting one of these electrophiles with the potassium dianion prepared from arylic alcohol 1, we added the second electrophile sequentially and then warmed the reaction temperature to room temperature. As a result, various alkyl halides such as aryl bromide, benzyl bromide, propylylic bromide, methyl bromoacetate, and bromoacyl nitro, as well as aldehyde and disulfide were successfully induced at the alpha position in good yield. We then attempted to synthesize C3 functionalized silyl ethers. A variety of electrophiles were reacted with the potassium dianion, and the resulting potassium enolate were trapped with silyl chloride. Various silyl ethers were obtained by the reaction with aldehyde, imines, 1,11-amide, and dimethylformamide, followed by addition of test chloride and TIPS chloride. Other electrophiles such as alkyl halides, activated alkenes, epoxide, and enones could also be used. In addition, heteroatom-based electrophiles also available for use, and corresponding products were obtained in good yield. The resulting C3 functionalized cyclinyl ether can be converted to alphabet difunctionalized ketones by combining with various alpha functionalization reactions. For instance, compound 1 can be transformed into difunctionalized ketone 2 and 3 through electrophilic fluorination or lobotomy oxidation. Furthermore, compound 4 can provide 5 through kappa catalyzed elevation, and subsequent parallel reaction can convert it into multi-substituted furans or pyrroles. The research results presented today are the outcome of the tremendous efforts of the students in our research group. This achievement would not have been possible without their dedication. I'd like to take this opportunity to express my deep gratitude to them. Thank you for your attention.
Sai, for your nice talk on earth abundant metal mediated reactions. So maybe audience invite any 1 or 2 questions. No more.
Only one small clarification. Yeah, what we call work. Other than potassium, did you try any other alkali or alkaline earth metal as a kind of what do you call a similar kind of an approach?
Pardon?
Other than the potassium, have you tried any other alkali or alkaline earth element as a kind of a catalytic approach?
Other potassium bases?
No, other than potassium. Other than potassium.
I also tested the lithium and sodium.
Yes.
Lithium and sodium are explored the reactivity, but these bases are totally ineffective for the reaction.
What could be the reason for it? What could be the reason for it? What could be the reason?
Reason? Because of the basicity. Potassium, potassium is more basic than corresponding lithium bases or sodium bases. So only potassium bases are effective for this reaction.
Okay, fine. Thank you.
Thank you, Professor Sai, for your lecture. Maybe
Professor Mukherjee has one question.
Yeah, Professor Mukherjee, you can just ask.
Yeah, thank you. Thank you, Professor Sai, for very nice work. Actually, I really like the concept of dianion. In your slide 24, where we exchange the metal, yeah. So I can see 2 different reactive sites, like with the lithium, you got at the beta position, whereas with zinc chloride, you got at the ipso position. So does it depend on the electrophile, or it is just which metal you are replacing with?
Zinc is more less acidic compared to lithium or potassium. So in this case, I think, yeah, zinc is more less acidic, so zinc acts as a less acid to coordinate to the oxygen atom of some chloride, acid chloride. Okay. So the reaction occurs at this 6 members transition state, and this position, this carbon attacks the acid chloride. So the branched product was obtained, I think.
Okay, so in the first case where you had the lithium bromide, if you use the benzoyl chloride, will it go to the beta position in this case?
Yeah, I think so, but I didn't try.
Okay, all right.
Thank you.
Thank you.
Okay, thank you, Sai.
Okay, so thank you, Dr. Adimukti. So finally, we have arrived at the end of the webinar, actually. So thank you, Shai Sensei.
Thank you very much.
Yeah. So before we close, I'd like to formally give the vote of thanks of the event. So at first, I'd like to thank our director, sir, Dr. Kannan Srinivasan, for kindly agreeing to host this program at CSMCRI and providing all required supports to make it a grand success. So this event would not have been possible without the kind support and able guidance of our director, sir. So I wholeheartedly thank Professor Shakti Kumar, President IJA, and Professor Utpal Bora, General Secretary IJA, to come up with the proposal to organize the event in the west part of India, such as in our institute. And subsequently, when I proposed to this to our director, he immediately accepted the request and extended all supports towards the success of the event. So I thank you, sir, for the kind approval of this event. And I'd like to thank all the esteemed speakers, Professor Devabrata Maiti, Professor Kazuaki Ishihara, Professor Shantanu Mukherjee, Professor Ujiro Hayashi, Professor Biplab Majhi, and Professor Masahiro Shai for kindly agreeing to deliver the lectures. And I'm grateful to all of them, particularly to note that in spite of having a lot of important works in their regular schedule, they have kindly agreed to deliver the lecture here. And I'm sure that the researchers in the field have been benefited from their spectacular lectures. So thank you once again. I'd like to thank all chairpersons of today's webinar, Dr. Bishojit Ganguly, Dr. P.S. Subramanian, and Dr. S. Adimurthy, to kindly chair the technical sessions. Since the morning, they have been continuously sitting in this conference room to chair all the sessions, in spite of having their other work. So I'm really thankful to all of them. And I'm also thankful to the IT support team, particularly Mr. Pramod Makwana and Mr. Pradeep Kumar, CSMCRI, to nicely organize the webinar and continuously giving us support from the backstage to smoothly run the event online. I also thank our supporting staffs of CSMCRI. Finally, I'd like to thank each and every participant of today's webinar to actively take part in this event and listening to the lectures carefully. So thank you very much for your time and kind attention. So the event is now officially concluded here. Thanks for joining us today. We hope in the future we will arrange some more events. Thank you all.
Thank you, Sukallan. Fantastic event.
Thank you, Shantanu.
Thank you all.
Thank you, Biplav.
So thank you very much.
Thank you, Professor.
Thank you.
Bye-bye.
Thank you, everyone. Thank you, Sukallan.
Thank you, Sai-san. How are you?
I'm nice.
Long time.